Smarties, M&Ms, and Astros are candy-coated powerhouses built for color and perfect melt. Inside fast-moving confectionery plants, chocolate centers are formed and cooled until every piece looks camera-ready. Today, we step onto the production floor to see how mixing and high-speed sorting create that signature snap, and how factories keep every batch uniform down to the last candy. Smarties are produced by making small, lens-shaped chocolate centers, then building a thick, crunchy sugar shell through repeated syrup and drying cycles, then applying color as controlled surface layers, then polishing the finished pieces so they handle cleanly in high-speed packing. Chocolate for the center is prepared as a fat continuous suspension where sugar and milk solids are dispersed finely in cocoa butter. Dry ingredients are first blended so they enter refining at a steady ratio. The blend is refined through roll refiners or similar mills that reduce particle size until the texture target is reached. The refined flakes move into conching, where heat and shear redistribute fat and reduce residual moisture. Conching also drives off sharp volatiles and smooths flavor by rounding the chocolate matrix. After conching, the chocolate is tempered to create the crystal form that solidifies quickly and resists bloom during later handling. Center shaping follows tempering because the centers must be uniform in mass and curvature. One common method uses depositing into multi-cavity molds shaped as shallow domes. The tempered chocolate is dosed by volumetric pistons, and the mold is vibrated so trapped air rises and the surface settles. Cooling tunnels then pull heat out in stages so the centers contract and release cleanly. Another method uses a depositing belt where small portions are dropped onto a cooled steel band and then shaped by calibrated rollers that create the characteristic lens profile. Both methods aim for the same outcome. Each center must have consistent diameter and thickness because shell growth depends on how the pieces roll in the pan. After demolding or belt release, the chocolate centers are conditioned. Conditioning brings the centers to a stable temperature where the surface is firm and dry. If centers are too warm, they smear when they collide. If centers are too cold, they can chip at the rim. Conditioning also reduces moisture condensation risk because any surface moisture would interfere with the first sugar layers. The next phase is panning, which is the core of Smarties manufacturing. The centers are loaded into rotating coating pans or perforated drums. Rotation creates a circulating bed where pieces climb the wall, then roll down in a controlled cascade. The cascade is tuned by drum speed and fill level. The goal is continuous rolling rather than sliding because rolling exposes every surface evenly to syrup and air. Shell building starts with an adhesion stage that acts like a primer. A light syrup is atomized into the moving bed. Droplets land and form a thin, wet film on the chocolate surface. Dry air immediately follows and removes water, so the film becomes tacky, then crystalline. This first layer must bond strongly without dissolving the chocolate surface. Bond strength is created by using low application volumes and by setting the layer quickly before pieces can stick together. Once adhesion is established, the process shifts to thickness build. A higher solid syrup is sprayed in measured pulses. Immediately after spraying, fine sugar is introduced in a controlled dusting step. The powder absorbs surface moisture and raises the solids at the interface. Airflow then dries the layer and forces crystallization through the shell thickness. This sequence is repeated many times. Each pass adds a small amount of mass and the shell grows gradually. The process manages 3 linked variables during build. Syrup solids determine how fast the surface sets. Spray droplet size determines coverage uniformity. Drying air conditions determine how crystals form. If drying is too aggressive, the surface can harden while moisture remains inside. That trapped moisture later causes pitting or weak spots. If drying is too gentle, the surface stays sticky and pieces can form twins. Twin formation is prevented by keeping the bed in motion and by matching spray timing to drying capacity. As layers accumulate, the shell becomes strong enough to take higher mechanical loads. Drum speed can be increased slightly to improve rounding. Too much impact will chip edges so the adjustment is small. The sound of the bed changes as hardness increases. Early in the run, the cascade sounds soft because surfaces are damp. Later, it becomes sharper because shells are glassy. This acoustic shift tracks the build progress and can be used as a practical process signal. Shell texture is refined continuously. Early layers tend to be rough because crystals nucleate quickly on the primer. Later layers are used to smooth those imperfections. Smoothing is achieved by reducing powder addition and relying more on thin syrup films that flow into micro valleys. Longer drying times then lock the smoother surface. This is also where the roundness improves because small ridges are worn down by rolling contact. Color development is treated as a separate surface engineering step rather than a single dye addition. Color solutions are prepared at controlled concentration and filtered so no particulates enter the spray system. The colored liquid is applied in very thin coats. Each coat is dried fully before the next one. Multiple light coats create saturation without streaks. A heavy single coat would pool in low spots and create blotches. Color is usually introduced after the shell has reached most of its thickness. That timing protects chocolate from moisture and prevents color from being buried under too many later clear layers. Even so, the sequence often includes a few structural coats after the first color, passes. These coats help lock pigment into the surface and reduce rub-off. The process can alternate between tinted syrup and clear syrup, depending on how quickly saturation rises. When multiple colors are produced, the line typically runs one color per batch. That keeps the shade consistent and prevents cross-contamination in recycle streams. Changeover includes flushing spray lines and cleaning pan surfaces, so the next color does not pick up residue. Color measurement is performed on samples and compared against a target. If shade is light, the process adds extra passes. If shade is dark, the process reduces concentration or shortens the color stage. After color is complete, the shell is given a final hardening sequence. Hardening uses clear syrup in very small amounts with longer drying time. This reduces surface porosity and increases hardness. The aim is a shell that cracks cleanly when bitten, but does not chip during conveying. Hardness is strongly tied to moisture, so the process drives moisture to a defined endpoint rather than to the lowest possible value. Moisture equalization follows hardening. Even when the surface is dry, the inner shell can retain slightly higher moisture. Equalization holds the product in controlled air, so moisture gradients flatten. This reduces internal stress that can cause fine crazing lines. It also stabilizes the surface for polishing, because polishing films spread best on a consistent substrate. Polishing is then performed in a separate pan with gentler motion. A polishing agent is applied as a very fine mist. The pieces tumble and the film spreads by repeated contact. The film fills micropores and reduces surface friction. This creates the familiar gloss and also improves flow through packaging machinery. Polishing is kept light because excessive polish can feel waxy and can reduce color brightness. After polishing, the pieces are cooled and rested briefly. This allows the polish film to set and reduces tack. Dust extraction can be used at this stage to remove loose sugar particles. Loose dust is undesirable because it dulls gloss and can contaminate package seals. Sorting and classification come next because shell products create fragments and twins even with good control. Vibratory screens remove fines and broken shell chips. Size classification can remove off-size pieces that would stand out visually. Optical sorting can reject twins and pieces with exposed chocolate where shells chipped. Sorting is tuned to protect throughput while removing defects that would impact appearance and crunch. The finished Smarties then move to packing through gentle handling systems. Drop heights are minimized because even a hard shell can chip at the rim. Chutes are designed with smooth curves rather than sharp edges. Hoppers are designed to avoid bridging and to keep flow stable. If the line uses vibratory feeders, the amplitude is kept low to avoid abrasion. Portioning is usually done with multi-head weighers because the product flows as discrete pieces. The weigher distributes candy into many small hoppers. A control system selects combinations to hit the target weight precisely. The selected portion drops through a funnel into the primary package. The funnel geometry is designed to reduce bounce and to prevent pieces from striking the seal area. M&Ms are produced by forming uniform chocolate-based centers, then building a hard sugar shell through controlled panning cycles, then applying color and a final gloss coat before high-speed packaging. Center manufacture starts with chocolate preparation because the center defines final size and how the shell grows. Chocolate ingredients are blended into a fat continuous mass where sugar and milk solids are dispersed. The mass is refined to reduce particle size and eliminate grit. Conching follows to redistribute fat and reduce moisture while smoothing flavor. Tempering then sets the cocoa butter crystal form so the centers solidify quickly and remain stable during shell building. Centers can be plain chocolate or can include inclusions depending on format. For plain centers, the tempered chocolate is deposited into molds or onto a cooled belt. Molded centers use multi-cavity molds shaped as small domes. Depositing systems meter a precise mass into each cavity, and vibration removes trapped air. Cooling tunnels then solidify the chocolate until it releases cleanly from the mold. Belt-deposited centers are dropped as small buttons and then shaped by controlled vibration or light rolling to create a consistent pellet. When inclusions are used, they are incorporated during depositing. Nuts or crisp pieces are pre-sized and coated lightly so they do not shed fines. Inclusion dosing must be consistent because it changes mass and shape. The chocolate must wet the inclusion surface and then set without voids. Void-free centers roll more predictably in panning and resist cracking. After forming, the centers are conditioned. Conditioning brings temperature into a narrow band where the chocolate is firm but not brittle. If centers are too warm, they deform under tumbling loads. If too cold, they chip at edges and create sharp points that can pierce the shell. Conditioning also stabilizes surface moisture, so the first sugar layers bond consistently. Shell building uses rotating pans or perforated coating drums. Centers are loaded to a defined bed depth. Drum speed is set so the pieces roll continuously and do not slide. Rolling is essential because the shell grows by repeated thin layers that must distribute evenly around each piece. The first shell layers act as a sealing and adhesion stage. A thin syrup is sprayed onto the rolling bed. The syrup wets the chocolate surface and forms a sticky film. Dry air then removes water so the film crystallizes and locks on. This stage must be gentle because too much liquid can dissolve the surface or cause pieces to stick. Small additions, followed by full drying, create a stable base for thicker layers. After adhesion is established, the process shifts to bulk shell growth. A higher solid sugar syrup is sprayed in pulses. Immediately after spraying, a fine sugar powder can be dusted over the bed. Powder absorbs surface moisture and accelerates setting. Drying air then drives water out and promotes crystal growth through the layer. This spray dust dry cycle repeats many times. Each cycle adds only a small mass, so stresses do not accumulate. Drying control is critical because sugar crystallization defines hardness and surface quality. If drying is too rapid, the surface can harden while internal moisture remains. Trapped moisture later creates pitting or weak shells. If drying is too slow, the surface stays tacky and pieces can twin. Twin pieces stick and create double shapes that cannot be sold. Air temperature and humidity and airflow rate are tuned so each layer sets fully before the next spray. As the shell thickens, the process adjusts. Mechanical intensity. Early on, the bed motion is gentle to avoid deforming centers. Later, the shell is strong enough for slightly higher speed, which improves rounding. Excess speed creates chips, so adjustments remain small. The objective is a near spherical shape for standard M&Ms. Shape uniformity helps printing and improves flow in packaging. Shell thickness is monitored by mass gain and by size checks. The line targets a final shell to center ratio that controls crunch and dissolution time. Too thin a shell yields soft bite and color rub. Too thick a shell yields excessive crunch and longer dissolve. Thickness control is achieved by counting cycles and controlling syrup solids and spray rate. When the shell is near final thickness, the process transitions to smoothing layers. Smoothing uses lower spray volumes and less powder. Thin syrup films flow into micro roughness created during bulk build. Longer drying times then lock a smoother surface. Smoothness matters because it improves gloss and makes the final printed mark sharp. Color application is done as a sequence of thin coats. Color solutions are prepared at controlled concentration and filtered. Color is applied by spraying a tinted syrup or a color solution onto the rolling bed. Drying follows after every pass. Multiple light passes build saturation without streaking. Heavy application would pool in low spots and create blotches. Different colors are normally processed in separate runs to prevent cross-tint. Changeover includes flushing spray lines and cleaning pan surfaces. Shade control is performed by optical measurement. Adjustments can be made by changing concentration or by adding additional light passes. The final shade must be stable under polishing and handling. After color is established, the shell receives a protective clear finish. A clear syrup or glaze coat can be applied in thin layers. This coat smooths the surface and reduces pigment rub-off. It also creates a base for polishing. Drying after clear coats is extended to drive moisture to a stable endpoint. Moisture endpoint matters because residual moisture can cause stickiness and dull gloss. Polishing is performed after the shells have equilibrated. Pieces move into a polishing pan with gentler tumbling. A polishing agent is applied as a fine mist. The pieces roll and the film spreads and fills micropores. This creates the characteristic shine and reduces friction. Reduced friction improves flow through hoppers and reduces scuffing. Polishing must be controlled because too much polish can feel waxy and can interfere with printing. For marked M&Ms, the letter is printed near the end of finishing. Printing uses edible ink transferred by a pad printing system. The candies are fed into a positioning system that presents a stable face. The pad picks up ink from an etched plate and transfers it to the candy surface. Ink viscosity and pad pressure are tuned so the mark is crisp. The surface must be dry and smooth for good adhesion. After printing, the pieces pass through a short drying stage so the ink sets. Conditioning after printing stabilizes the finished shell. This stage allows moisture and temperature to equalize and reduces internal stress. Stable conditioning improves resistance to cracking during packaging. It also ensures the polish and ink films are fully set. Sorting and screening remove defects before packaging. Vibratory screens remove fines and broken pieces. Optical sorting can remove twins and off-color pieces and pieces with missing print. Size grading ensures consistent diameter. These steps improve appearance and also protect packaging machines from jams. Conveying to packaging is designed to minimize impacts. Drop heights are kept low and chutes are smooth. Hoppers are designed to prevent bridging. Feeding systems deliver a steady flow to weighers. Excess vibration is avoided because it can chip shells and generate dust. Portioning uses multi-head. Weighers for bag formats. The candies are distributed into many small hoppers. Software selects combinations that meet target weight. The portion drops through a funnel into a bagging machine. Bagging uses vertical form fill-seal systems, where film becomes a tube and seals are made above and below the drop. Seal timing keeps candies out of the seal area. Barrier films protect against moisture, which would soften shells and dull gloss. For tube formats, the process may use counting or volumetric dosing. A counting system uses sensors to count pieces as they fall into tubes. Volumetric systems use cups that measure a defined volume. Tubes are capped and then labeled. For carton formats, the candies are dosed into cartons, and the cartons are closed and glued. Each format relies on consistent flow and low dust. Case packing groups finished units into shipping cases. Cases are sealed and coated. Palletizing stacks cases to reduce movement. Storage conditions are held stable to protect. Chocolate and shell. Temperature swings can cause chocolate expansion and contraction, which stresses the shell. Stable conditions reduce cracking and help maintain gloss. Astros are manufactured by forming small chocolate-based centers with tight size control, then building a hard sugar shell in rotating pans, then applying color and a final gloss so the pieces pour cleanly and resist scuffing. Center production starts by creating a stable chocolate mass with the right flow and snap. Cocoa solids, sugar, and milk solids are combined with cocoa butter and mixed until the powders are fully wetted. The mixture is refined to reduce particle size, so the center feels smooth rather than gritty. Conching follows, where heat and shear drive off residual moisture and redistribute fat, so viscosity becomes predictable. The chocolate is then tempered, so cocoa butter crystallizes in a stable form that sets fast and resists bloom. This temper step matters because centers must survive long tumbling. Cycles without softening or smearing. Center shaping is designed around uniform mass and consistent curvature. Tempered chocolate is deposited in precise portions, either into shallow dome molds or onto a cooled steel belt. Mold depositing uses metered pistons that deliver the same dose every time. Vibration removes trapped air and levels the surface, so each center has the same profile. Belt depositing forms small buttons that are shaped by controlled vibration or light rolling. Both approaches aim for the same lens, like pellet that will roll evenly in a coating pan. When inclusions are used, the inclusion stream is stabilized before it touches chocolate. Crisp pieces or nut fragments are screened to a narrow size band. Fines are removed because they make dust and create weak spots in the center. The inclusions are then kneaded into chocolate at a controlled ratio. The chocolate must flow around each inclusion and fill voids. Voids create weak points that later crack under shell, stress. After forming, the centers are cooled in stages. Early cooling pools heat out quickly to lock shape. Later cooling slows down to reduce internal stress. A controlled cooling profile produces centers that release cleanly and have consistent hardness. The centers then enter conditioning, where temperature is brought to a stable range for panning. Centers that are too warm deform during tumbling. Centers that are too cold chip at the rim and create sharp edges that can pierce the shell. Shell building begins in rotating coating pans or perforated drums. The pans are loaded to a defined bed depth, so the pieces roll in a continuous cascade. Rotation speed is tuned so pieces roll rather than slide. Rolling ensures every surface sees the same spray and drying exposure. Sliding creates flat spots and uneven layer thickness. The first shell layers are an adhesion stage. A light sugar syrup is atomized into a fine mist and applied in short pulses. The syrup wets the center surface and forms a thin film. Dry air follows immediately and drives off water, so the film crystallizes and locks in place. This stage must avoid excess liquid because wet centers stick together and form twins. It also must avoid slow drying because tack persists and collisions bond pieces. After adhesion, the process shifts to bulk shell growth. A higher solid syrup is sprayed onto the rolling bed. Fine sugar is often dusted on top of the wet film. The dust absorbs moisture and speeds setting. Airflow then dries the layer and drives crystallization through its thickness. This spray, dust, and dry cycle is repeated many times. Each cycle adds only a small amount of mass, so the shell builds gradually without large stress jumps. Crystallization control drives shell strength and surface quality. If drying is too aggressive, the surface can harden fast while moisture remains inside the layer. That trapped moisture later escapes and forms pits or weak spots. If drying is too gentle, the surface stays. Sticky and pieces can clump. Air temperature and humidity and airflow rate are tuned, so each layer sets fully before the next spray. Syrup concentration is also controlled because higher solids set faster, but can create roughness if they crystallize too quickly. As the shell thickens, the process adjusts how it manages shape. Early on, the bed motion stays gentle because the center is still close to the surface and can be damaged. Later, the shell has enough thickness to take slightly more impact. Increased rolling helps round the pieces and smooth high points. Impact must still be limited because chips create exposed layers and color defects later. Shell thickness is managed by mass gain and by dimensional checks. The line targets a shell to center ratio that defines crunch and dissolve time. A shell that is too thin will scuff and show color rub. A shell that is too thick will feel overly hard and can crack when bitten. Thickness is tuned by the number of build cycles and by syrup, solids, and spray rate. Surface refinement starts when thickness is near target. The process reduces powder addition and uses thinner syrup films. Thin films flow into micro valleys and smooth the texture. Longer drying times then lock the smoother surface. Smoothness is important because it improves gloss and reduces abrasion in packaging. It also supports sharp color appearance because rough surfaces scatter light. Color is applied as controlled outer layers rather than as a single heavy coat. Color solutions are prepared in mixing tanks with tight concentration control. They are filtered so no undissolved particles reach spray nozzles. Color is applied in light passes and dried fully after each pass. Multiple passes build saturation without streaks. Heavy color application would pool and create blotches. Light passes allow the bed motion to distribute color evenly. Color timing matters. Applying color too early risks burying pigment under later structural layers. Applying color too late risks poor adhesion because the shell surface is already very hard. Many lines introduce color after the shell has most of its thickness and still has enough surface receptivity. Then they lock color with a few clear layers that reduce rub-off and improve durability. When multiple colors are produced, the process usually runs each color in separate batches. Separate runs reduce cross-tint and keep shade consistent. Between colors, the spray system is flushed and the pan interior is cleaned to remove residual pigment. Shade checks are performed on samples. Adjustments are made by changing pass count or concentration. The goal is a tight shade window across the entire run. After color, the shell receives a protective finish stage. Clear syrup coats can be applied in very small amounts. These coats smooth the surface further and help protect pigment. Drying after clear coats is extended to reach a stable moisture endpoint. Moisture endpoint is critical because residual moisture causes stickiness and dull gloss. Too little moisture can make shells brittle and prone to chipping. Moisture equalization follows the final drying. Even when the surface feels dry, the inner shell can hold a slightly different moisture level. Equalization holds the product in controlled air so gradients flatten. This reduces internal stress that can show up as fine cracking. It also stabilizes the surface for polishing because polish spreads best on a consistent substrate. Polishing creates the characteristic shine and improves flow. Polishing is done in a separate pan with gentler tumbling. A polishing agent is applied as a fine mist. The pieces roll and the film spreads across the surface through repeated contact. The film fills micro pores and reduces friction. Reduced friction lowers scuffing and improves how the pieces move through hoppers and chutes. Polishing must remain controlled. Too little polish leaves a matte surface that sheds sugar dust. Too much polish can feel waxy and can increase slip in handling. The process, therefore, uses small additions with extended tumbling between them. This lets the film distribute evenly and avoids wet spots that would cause clumping. It all starts with the base formula, the gummy candy itself. The core of every Sour Patch Kid is a soft, chewy matrix primarily composed of sugar, corn syrup, gelatin, and various fruit flavors. These ingredients must be blended in precise proportions to achieve the specific texture that Sour Patch Kids are known for. Not as firm as gummy bears, not as sticky as fruit snacks, but perfectly chewy with a fast melt in the mouth. The sugar and corn syrup form the bulk of the candy. Sugar provides structure, sweetness, and contributes to the candy's crystal clear translucence, while corn syrup prevents the sugar from recrystallizing and keeps the final product soft and elastic. These two are delivered to the factory in bulk. Sugar often in railcars or tanker trucks, and corn syrup in heated stainless steel tankers to maintain fluidity. In the batching area of the facility, massive stainless steel mixing kettles are used to combine sugar, corn syrup, and water. The mixture is heated to dissolve the sugar and initiate cooking. Industrial mixers stir the solution constantly, while steam-jacketed walls evenly raise the temperature to around 230 degrees to 250 degrees, depending on the desired consistency and final moisture content. At this stage, the mixture is highly viscous, resembling hot, liquid sugar syrup. Once the sugar solution is properly cooked, gelatin is added. Gelatin is the key protein that gives Sour Patch Kids their elastic chew. It's derived from collagen, typically from pork or beef, and arrives at the factory as a dry powder. It is hydrated in warm water in separate tanks and added to the sugar syrup only after the syrup has cooled to an appropriate temperature to avoid denaturing the gelatin. This step transforms the hot sugar mixture into a viscoelastic candy base. At this point, citric acid and tartaric acid are introduced. These two organic acids are what provide that first intense sour kick when you bite into a Sour Patch Kid. They are used at very specific levels. Too little, and the candy loses its iconic tang. Too much, and the texture or shelf stability may be affected. Food scientists spend years perfecting this balance. In addition to acidulants, artificial and natural fruit flavorings are also added, usually concentrated solutions of compounds that mimic cherry, lemon, lime, orange, blue raspberry, and other classic flavors. Color is next. Each flavor of Sour Patch Kid is dyed with specific food-grade colorants. These are either synthetic or naturally derived, like beet juice or turmeric extract, depending on the formulation and market regulations. These colorants are added to the mix during the blending phase in tightly controlled amounts to ensure vibrancy and uniformity across batches. Once the hot candy mixture is fully mixed, it is ready to be molded. Sour Patch Kids are molded using a starch mogul system, a technique used for generations in gummy candy manufacturing. The starch mogul line begins with large trays filled with cornstarch. These trays pass under a stamping head fitted with dozens of Sour Patch Kid-shaped molds. The stamps press into the starch, forming hundreds of identical candy-shaped impressions per tray. The hot, syrupy candy mass is poured into these impressions using heated depositors. The candy flows smoothly into each cavity, forming the familiar, tiny humanoid shape. These trays, now filled with thousands of candy molds, are stacked and moved into drying rooms, also known as curing chambers. Here, the candies rest for 24 to 48 hours in warm, dry conditions. The cornstarch helps wick away moisture from the candy, allowing it to firm up without collapsing or becoming sticky. During this curing period, the gelatin sets fully, giving each candy its final chewable texture. After curing, the trays are sent to a destarching station. Here, the starch is separated from the candies using rotating sifters and vibration tables. The excess starch is collected, filtered, and reused in future molding cycles. The Sour Patch Kids, now fully formed and firm, are tumbled through gentle conveyors to remove residual starch. Now comes the most distinctive part of the process, the sour sugar coating. This is what gives Sour Patch Kids their unique mouth-watering appeal. The coating consists of a blend of fine granulated sugar, citric acid, and tartaric acid. The finished candies are placed into large rotating pans or coating drums, similar in appearance to cement mixers, but designed specifically for food products. As the drums rotate, the candies tumble over one another, while a fine mist of water or sugar solution is sprayed lightly to help the sour powder adhere. Simultaneously, the sugar acid blend is sprinkled in. The result is a uniform, crystalline coating on every piece. Timing and rotation speed are key here. Too much coating and the candy becomes overwhelming and sticky. Too little and the signature tang is lost. Factory technicians carefully monitor coating weights and perform quality checks throughout the shift to ensure product consistency. After coating, the candies are passed through a drying tunnel or cooled in ambient air to set the coating. They are then conveyed to an inspection area where cameras, sensors, and sometimes human inspectors check for shape, color, and coating uniformity. Any malformed or off-spec candies are removed from the line. Now it's time to package the final product. Sour Patch Kids are typically packed into portioned pouches, multi-serve bags, or retail cartons. The packaging line begins with form-fill-seal machines, high-speed systems that unroll printed plastic film, form it into pouches, fill each pouch with a measured weight of candy, and then seal it shut using heat. These machines are calibrated to ensure each pack contains the right amount of product and is sealed airtight for freshness. The sealed pouches are then coded with date stamps, batch numbers, and sometimes QR codes for traceability. They are dropped into shipping cartons or display cases, depending on the destination. These cartons are weighed, barcoded, and stacked automatically onto pallets. From there, the pallets move to temperature-controlled warehouses, where they await shipment to stores, vending distributors, movie theaters, and supermarkets. Throughout the factory, food safety is the top priority. Every step, from ingredient receiving to packaging, is conducted under good manufacturing practices. Workers wear protective clothing, hairnets, and gloves. Equipment is cleaned between production runs. Acid-resistant stainless steel and food-grade plastics are used throughout the facility. Environmental controls manage humidity and air filtration to ensure cleanroom-level hygiene in production zones. Sour Patch Kids production also involves detailed analytical testing. Random samples are pulled from each batch and tested in quality control labs for pH, moisture content, acid levels, color uniformity, texture, and shelf life stability. Sensory panels evaluate flavor consistency and sour-sweet balance. If any parameter is off, adjustments are made in the next batch, or the lot is held for investigation. As candy demand has grown, the process has become even more efficient through automation and smart technology. Modern factories use real-time data monitoring systems to control temperatures, mixer speeds, and depositor rates. Predictive maintenance software ensures machinery stays operational. Ingredient inventory is tracked digitally, and computerized dosing systems eliminate human error in weighing acids or colorants. Sustainability has also become a key consideration. Factories producing Sour Patch Kids increasingly aim to reduce water use, lower energy consumption, and source gelatin from suppliers who practice ethical sourcing. Even the packaging films are being redesigned in some regions to be recyclable or biodegradable. When the candy finally reaches store shelves, it has already traveled a long journey, from raw gelatin and sugar to the smiling, sour-coated figures we all recognize. Each bite delivers not only flavor, but the culmination of chemistry, engineering, and candy artistry. The sour then sweet experience isn't just a slogan, it's a precisely engineered sensory journey that begins with a sharp, puckering acid hit and fades smoothly into fruity, mellow sweetness. The process begins with the core ingredients: sugar, corn syrup, water, flavorings, and colorants. These are the building blocks of Jolly Ranchers, but the way they are combined and treated in the factory determines the final product's success. Sugar and corn syrup are delivered in bulk to the manufacturing plant, sugar often in powder or granulated form, and corn syrup as a thick liquid shipped in insulated tanker trucks to keep it warm and flowable. In the batching room, large stainless steel kettles are used to combine sugar, corn syrup, and a small amount of purified water. The goal is to dissolve the sugar and initiate a high-heat cooking process that transforms these ingredients into a highly concentrated, clear candy base. This cooking step is key. Jolly Ranchers are a type of hard candy, which means the sugar mixture must be cooked to what's known in confectionery as the hard crack stage, around 300 degrees to 310 degrees. These cooking kettles are jacketed with steam coils or electric heating elements that allow precise temperature control. As the mixture heats, the water begins to evaporate and the syrup thickens significantly. This evaporation is critical. It's what ultimately leaves the candy with such a low moisture content that it becomes glassy and brittle once cooled. Industrial stirrers keep the mixture agitated to ensure even cooking and prevent hot spots or scorching. As the syrup approaches the target temperature, automated sensors closely monitor the heat and viscosity. If the temperature is even slightly off, the final texture of the candy could be compromised. Undercooked syrup results in a sticky or chewy texture, while overcooked syrup becomes too brittle or may develop a burnt flavor. Once the sugar syrup reaches the perfect consistency, it's time to add the key components that give Jolly Ranchers their personality: flavor and color. The candy base is divided into smaller batches, each destined to become a different flavor: cherry, watermelon, green apple, blue raspberry, grape, and others. Each batch is transferred to flavoring tanks or mixing troughs where concentrated food-grade flavorings and dyes are added. These flavor compounds are highly concentrated and added in very specific ratios. Natural and artificial flavorings are used depending on the formulation. For example, a cherry Jolly Rancher might include benzaldehyde for that sharp, almond-like cherry punch, while green apple flavor could rely on malic acid esters for its tart kick. The colorants are also carefully chosen to match the expected visual identity of the flavor. Red 40, yellow 5, blue 1, and other FDA-approved synthetic dyes are often used in varying combinations to produce the vivid hues. Mixing must be fast and efficient at this stage because the candy syrup is still extremely hot and starts cooling quickly. Mixing arms or ribbon blenders integrate the flavor and color without introducing air bubbles, which would compromise the candy's clarity and structure. At this point, the flavored and colored syrup begins to thicken rapidly and takes on the consistency of hot, pliable taffy. Timing is critical. If it sets too quickly, it becomes unworkable. The next step is forming. Unlike many other candies that are molded in starch trays, Jolly Ranchers are formed using a process known as rope forming and die stamping. The hot candy is transferred onto cooling tables or through temperature-controlled rollers where it is shaped into thick, cylindrical ropes. These ropes are slowly cooled as they pass through stainless steel rollers and conveyors. The goal is to bring the candy down to a workable temperature where it can be cut and stamped, but not yet hardened completely. Once the candy ropes are at the right consistency, they pass through a forming machine fitted with precision dies. These dies stamp and cut the candy into individual pieces, each with the familiar oblong pillow shape. The forming machine applies enough pressure to ensure a clean cut, but not so much that it distorts the candy's surface. This is a delicate operation, as the candy is beginning to crystallize and solidify rapidly. The cutters must be kept heated or treated with food-safe lubricants to prevent sticking and preserve the clean edges of the final product. After forming, The individual Jolly Ranchers move on to a cooling conveyor system. These long, slowly moving belts expose the candies to progressively cooler ambient air or cooled forced air, gradually lowering their internal temperature. This slow cooling is important to prevent cracking and to ensure the surface remains glossy. If cooled too quickly, internal stresses could form, making the candy brittle or causing it to become cloudy. Once fully cooled and solid, the candies head to the wrapping stage. Each Jolly Rancher is immediately wrapped in a specially designed waxed film or polypropylene-based wrapper that prevents sticking and maintains freshness. Wrapping machines operate at extremely high speeds, feeding candies into synchronized rollers that twist wrap or fold seal each piece. The wrappers are pre-printed with branding, flavor indicators, and batch codes for traceability. The wrapped candies are then collected into large bins or counted into packaging units. Depending on the product line, Jolly Ranchers might be bagged into share-size pouches, fun-size treat bags, or bulk cartons. Form-fill-seal packaging equipment handles this part, weighing exact quantities of candies, dropping them into bags formed from a continuous roll of printed film, then sealing the bags with heat to make them tamper-evident and shelf-stable. As the candies are packaged, quality control plays a key role throughout the process. Random samples are taken and tested for color accuracy, size uniformity, hardness, and moisture content. Hardness tests may involve durometers or similar equipment that measures resistance to pressure, ensuring the candy has the right glass-like firmness. Flavor panels may also evaluate taste intensity, checking for flavor balance and clarity. If a batch is found to be off-spec, it may be rejected, reworked, or diverted to secondary markets. Behind all this precision lies rigorous food safety protocols. Workers wear gloves, hairnets, and lab coats in production areas. Machines are sanitized regularly, and allergen controls are in place even though Jolly Ranchers typically contain no nuts, dairy, or gluten. Hazard analysis and critical control point systems are used to identify and mitigate risks at each step of the process. From the moment the sugar is received to the point where a wrapped candy is sealed in a bag, every movement is monitored and recorded for traceability. Additionally, modern Jolly Rancher production facilities are incorporating automation and smart factory technologies. Recipe management systems ensure precise ingredient dosing, and digital controls allow managers to adjust batch temperatures and cooking times from central dashboards. Optical sensors inspect wrappers for misprints. Even the temperature and humidity of production rooms are computer controlled to maintain consistent output regardless of the season or climate outside. Sustainability is also being addressed in newer production lines. Energy-efficient kettles and heat recovery systems help reduce fuel use. Water used in equipment cleaning or steam generation is recycled where possible. Wrapping materials are being developed with recyclability in mind, and many facilities are exploring biodegradable or compostable film options. The finished Jolly Ranchers, now bagged and boxed, are stacked onto pallets and moved into climate-controlled warehouses for distribution. These candies are remarkably stable, with long shelf lives due to their low moisture content and protective wrapping. This makes them ideal for global shipping. From there, they head to supermarkets, convenience stores, vending machines, and movie theaters all around the world, ready to deliver that unmistakable burst of sour cherry, green apple, or blue raspberry flavor. It all begins with the selection and preparation of the raw ingredients. At the core of every Haribo gummy candy is a combination of sugar, glucose syrup, gelatin, citric acid, fruit flavoring, and food coloring. These ingredients must be carefully sourced and managed to ensure the consistent taste, texture, and appearance that consumers expect. Sugar and glucose syrup form the base of the gummy. These are typically delivered to the Haribo factory in large quantities, sugar in bulk containers or silos, and glucose syrup in insulated tankers to maintain fluidity. In the production facility, the sugar and glucose syrup are fed into large stainless steel kettles equipped with steam jackets and stirring paddles. The mixture is gently heated and stirred to fully dissolve the sugar crystals, creating a thick, sweet solution. This sugary base is the fundamental building block for all Haribo products. Once the sugar solution reaches the appropriate concentration and temperature, gelatin is introduced. Gelatin is a key functional ingredient in Haribo gummies, providing their characteristic chewiness and structure. It is typically derived from pork or beef collagen and arrives at the factory in dehydrated granule or sheet form. Before it can be added to the sugar mixture, the gelatin is first hydrated in warm water in separate mixing tanks. Once fully dissolved, the gelatin is combined with the hot sugar syrup under controlled conditions. The resulting mixture is carefully heated to a precise temperature, usually around 150 to 160 degrees, ensuring full integration of the gelatin without degrading its gelling ability. During this step, any acids such as citric acid or malic acid are also added. These acids are responsible for the pleasant tang that balances the sweetness of the candy and enhances the fruit flavors. Next, the flavorings and colors are introduced. Haribo uses a range of natural and artificial fruit flavors to create its signature gummy taste profiles. Each flavor, lemon, orange, raspberry, pineapple, and apple, among others, is blended in concentrated liquid form and carefully metered into separate batches of the hot candy mix. Food-grade colorants are added alongside the flavorings, giving each candy its bright, transparent hue. The combination of flavor and color must be exact to meet Haribo's internal standards, and flavor technicians often perform sensory evaluations during production. With the flavored and colored syrup fully prepared, it is ready for the molding process. Haribo gummies are formed using a traditional confectionery technique known as starch molding, or the starch mogul system. This process begins with large trays filled with cornstarch. A molding board presses bear-shaped cavities into the surface of the starch, creating hundreds of individual molds per tray. The hot, viscous candy mixture is poured into these molds using automated depositors equipped with multiple nozzles. Each nozzle dispenses the exact volume of syrup needed to fill a single bare cavity, ensuring uniform size and weight across thousands of pieces. The trays are then stacked and transferred to a curing room, a warm, dry environment where the candies are allowed to set for 24 to 48 hours. During this curing period, the gelatin network solidifies, giving each gummy its final elastic texture. The starch not only supports the shape, but also absorbs moisture from the surface of the candy, helping to achieve the perfect skin. Once the gummies are fully cured, the trays are sent to a destarching machine. This piece of equipment gently tumbles the trays, separating the candy pieces from the cornstarch. Vibrating screens and air jets remove any excess starch, which is collected, filtered, and reused in the molding process. The newly formed gummies, now free of starch and fully set, are inspected and prepared for the next stage. Now comes the coating process, which adds shine and improves handling. Haribo gummies are typically coated with a thin layer of food-grade wax, such as carnauba wax or beeswax, and vegetable oil. This coating is applied in rotating drums or tumblers, where large quantities of gummies are gently mixed while a light mist of the wax solution is sprayed over them. The result is a glossy surface that prevents the candies from sticking together and enhances their visual appeal. The wax also serves as a moisture barrier, helping to preserve the candy's freshness during storage and transport. After coating, the gummies pass through a final inspection phase. This includes both visual inspections by trained staff and automated optical systems that check for shape uniformity, color consistency, and size accuracy. Any defective or malformed candies are removed from the line and discarded or recycled, depending on the facility's protocols. Next, the candies move on to the packaging line. Haribo uses a range of packaging formats, including peg bags, share-size pouches, single-serve packs, and multi-flavor assortments. The packaging process begins with high-speed form-fill-seal machines. Printed plastic film is unrolled and shaped into pouches, which are then filled with a precise weight of gummies. The bags are sealed using heated jaws that bond the plastic layers together, creating an airtight, tamper-evident package. The filled bags are then printed with production information such as batch number, expiration date, and sometimes promotional codes or QR codes for consumer engagement. They are packed into cartons, stacked onto pallets, and moved to the warehouse where they await distribution. Throughout this final stage, quality control teams monitor the sealing integrity, fill weights, and print accuracy to ensure compliance with product specifications. Behind the scenes, every Haribo production facility operates under strict food safety and quality assurance protocols. These include adherence to good manufacturing practices, hazard analysis and critical control points, and ISO quality standards. Production areas are cleaned regularly, equipment is sanitized, and every batch is traceable from raw ingredient to finished product. Samples are pulled at every stage and tested in on-site laboratories for pH, moisture content, texture, and microbial safety. Modern Haribo factories also make use of advanced automation and data analytics. Ingredient dosing is controlled by programmable logic controllers to reduce human error. Sensors monitor cooking temperatures, gelatin concentration, depositor output, and humidity levels in real time. Production managers can access digital dashboards to track performance metrics and respond quickly to any deviations. These innovations not only improve efficiency, but also support the consistency that Haribo is known for. As a global brand, Haribo also customizes its recipes and flavors for different regions. For example, gummies produced in Europe may use natural colorings derived from fruit and vegetable concentrates, while US products may include certified synthetic dyes. Flavors may also vary to suit local preferences, such as blackcurrant in the UK, mango in Asia, or sour varieties in North America. Despite these differences, the core manufacturing process remains largely the same across all Haribo facilities. Sustainability is another growing focus in Haribo's operations. The company has been investing in renewable energy, water conservation, and waste reduction across its factories. Ingredient sourcing increasingly considers environmental impact and animal welfare, particularly in the sourcing of gelatin. Packaging materials are being re-evaluated to include recyclable films and reduce plastic usage. When a bag of Haribo Gold Bears finally lands on store shelves, it represents a highly coordinated blend of traditional candy-making techniques and modern industrial precision. Each chewy bear is the product of strict formulation, controlled cooking, precise molding, and sophisticated quality checks. From sugar kettle to glossy, colorful treat, the journey of a Haribo gummy is a testament to the art and science of confectionery manufacturing. While the candies may be playful and whimsical, the process behind them is anything but casual. It requires the coordination of food engineers, quality control experts, maintenance technicians, flavor developers, and packaging specialists, all working together to ensure that every handful of Haribo delivers the same beloved taste and texture, whether it's made in Germany, the United States, or anywhere else Haribo operates. This level of consistency and care is what has allowed the brand to thrive for over a century, making Haribo gummies a global favorite that continues to delight generation after generation. The history of Nerds stretches back to the early 1980s, when they were first introduced to the market as a playful, intensely flavored treat unlike anything else in the candy aisle. The appeal lay in their irregular shapes, their bright colors, and their signature combination of sweet and sour notes. Behind the scenes, however, the magic is created not by whimsy, but by a carefully controlled industrial process. It all begins with the sourcing of raw ingredients. The foundation of Nerds is refined cane or beet sugar, which arrives at the factory in bulk deliveries, often in multi-ton silos or in large paper sacks that are emptied into storage hoppers. This sugar is highly refined to ensure purity, with a moisture content so low that it will not clump during storage or handling. Alongside the sugar come shipments of corn syrup, which acts as a binding and texturing agent, as well as citric acid and malic acid to provide the tartness that defines Nerds' flavor profile. The plant also receives concentrated flavor oils and powdered colors approved for food use. Each batch of these ingredients is tested in a quality control laboratory before it enters the production stream, ensuring compliance with both flavor and safety standards. The production of Nerds begins with a core, which is essentially a tiny granule of sugar that serves as the seed for the candy's build-up process. These seed crystals are often derived from slightly coarser sugar grains that have been screened to a uniform size. The real artistry begins in the heart of the coating pans, large rotating drums that are the beating heart of sugar candy manufacturing. Inside these stainless steel pans, the sugar seed crystals are gently tumbled as a fine mist of sugar syrup is sprayed over them. This syrup is prepared in a heated mixing tank, where granulated sugar is dissolved into water under controlled temperature, often in the range of 110 to 130 degrees Celsius, and then blended with a precise amount of corn syrup to control crystallization. The hot syrup flows through jacketed piping to prevent premature cooling before being atomized into a fine spray within the coating pan. As the syrup coats the tumbling seed crystals, it begins to harden upon contact with the cooler air inside the pan, forming a thin outer layer. Then, a light dusting of dry sugar is sometimes added to further build the surface and maintain separation between individual granules. This cycle repeats dozens or even hundreds of times, each layer adding microns of thickness to the growing candy piece. Operators closely monitor airflow, humidity, and drum rotation speed to ensure that the candies do not stick together or form unwanted lumps. During this stage, the irregular shapes that make nerds so distinctive begin to emerge. Unlike machine-molded candies that have identical geometry, these sugar coating pans produce slight variations in size and contour, which means every nerd has its own unique outline. The gradual layering process continues until the candy reaches the target size, which is typically just a few millimeters in diameter. Once the base size is achieved, flavoring and coloring are introduced. This is a delicate operation, as liquid flavors and colorants must be distributed evenly without dissolving the sugar surface. The pan operator reduces airflow slightly and sprays a concentrated solution of flavor oils, acids, and color onto the candy bed. In many cases, flavors are applied in small incremental sprays with pauses for tumbling in between, allowing the surface to dry and preventing color streaking. The flavors are carefully balanced so that the acids provide tang without overwhelming the sweetness, creating the signature taste that fans recognize instantly. After flavoring and coloring, the candies undergo a polishing step. This involves applying a thin layer of glazing agent, such as carnauba wax, which gives the nerds their characteristic sheen and helps protect them from moisture pickup during storage. The glaze is applied in a separate polishing pan, where candies are tumbled with a small amount of the molten wax until every piece has a uniform shine. At this point, the candies are allowed to cool and set fully, ensuring that their coatings have hardened completely. Cooling may occur in ambient air or in a temperature-controlled chamber that maintains low humidity to prevent stickiness. The fully cooled candies are then transferred via gentle vibratory conveyors to the packaging area. The packaging operation for nerds is an impressive example of precision weighing and high-speed filling. Because the candy pieces are so small and irregular, multi-head weighers are commonly used to ensure accurate portioning. These machines use multiple load cells arranged in a circular pattern, dropping small amounts of candy from each channel until the combined total matches the target weight. This system minimizes giveaway and ensures that each box contains exactly the promised amount. The iconic Nerds boxes are constructed from food-grade cardboard with an inner lining that protects against moisture. The packaging line begins by folding and gluing the flat-printed cartons into their box shape, often with automated carton erectors that can handle hundreds of units per minute. The weighers then deposit the precise quantity of candy into each box through stainless steel chutes. For dual flavor boxes, a partition is inserted inside the carton, and two separate weighing heads feed different candies into each side simultaneously. Once filled, the boxes pass through a closing station, where flaps are folded and glued shut, followed by a coding station that prints lot numbers and best before dates for traceability. The sealed boxes are then collated into larger trays or shrink-wrapped bundles for ease of handling in distribution. Quality control continues all the way through the process. In addition to the raw ingredient checks at the start, samples of candy are pulled from the line at regular intervals to assess flavor consistency, color uniformity, and physical integrity. The hardness of the coating is measured with specialized instruments, and the acidity levels are checked to ensure the sourness remains within the brand's signature profile. Metal detectors are integrated into the conveyor system to ensure no foreign materials make their way into the final product. From the packaging area, the candies move to the warehouse for distribution. Since Nerds are low in moisture and have a hard sugar shell, they are relatively stable during storage. However, they are kept in a cool, dry environment to maintain their texture and prevent color fading. Pallets of finished product are wrapped and staged for shipment to wholesalers, retailers, and export markets around the world. The journey from sugar seed to the vibrant, tangy pellets in your hand is a testament to how much engineering is hidden inside even the simplest candies. Each step, from syrup spraying in massive tumbling pans to the delicate flavor infusion and high-speed filling lines, is executed with precision to deliver the playful, crunchy experience that has kept Nerds popular for decades. Over time, manufacturing technology for Nerds has evolved to improve efficiency and consistency. Early production relied heavily on skilled operators adjusting pans by sight and sound. Today, advanced automation systems track humidity, airflow, and syrup application rates with sensors and feedback loops, ensuring that every batch meets exacting standards. The result is a product that remains faithful to its original flavor and texture while benefiting from modern advancements in food processing equipment. There is also increasing focus on sustainability in candy production. Many factories now recover and reuse heat from syrup cooking kettles, implement water-saving cleaning systems for coating pans, and work with suppliers to source sugar from more sustainable agricultural operations. Packaging too is being re-evaluated, with lighter materials and improved recyclability being considered for the future. What makes the production of Nerds especially fascinating is the balance between art and science. The process is rooted in classical confectionery techniques that date back centuries, yet it is executed on a scale and with a precision that only modern machinery can achieve. The slight variations in size and shape that give Nerds their charm are not flaws, but deliberate results of the panning process, embraced as part of their identity. The story of Twizzlers begins long before the candy reaches the factory floor. As with many mass-produced confections, the foundation is in the sourcing of high-quality raw materials. The primary ingredient is refined wheat flour, which gives Twizzlers their chewy, slightly bread-like texture. This flour arrives at the plant in bulk tanker trucks and is stored in towering silos that protect it from moisture and contaminants. From here, it is gravity-fed or pneumatically conveyed through sealed pipes to the mixing area. Alongside flour, the recipe calls for corn syrup, which provides sweetness, binding power, and flexibility, as well as sugar, which boosts flavor and adds structure. Vegetable oil, often in the form of soybean or palm oil, contributes to the mouthfeel, while food-grade colors and flavorings give Twizzlers their signature appearance and taste. Every ingredient undergoes rigorous inspection in the quality control laboratory before it can be released to production. Flour samples are checked for protein content and moisture levels. Sugar is screened for crystal uniformity, and corn syrup is tested for viscosity and purity. Liquid flavors and colors are reviewed for consistency against reference standards. Once approved, ingredients move into the blending stage, where the transformation from raw material to candy dough begins. The mixing process takes place in large stainless steel horizontal mixers fitted with heavy-duty paddles or spiral blades. The operation starts with a precise ratio of flour and sugar being combined followed by the gradual addition of corn syrup and water. These mixers operate under controlled speeds to ensure the dough develops evenly without excessive heat buildup. Oil is incorporated next, coating the flour particles and contributing to the dough's smooth, pliable consistency. Throughout mixing, operators monitor temperature and dough texture, making small adjustments to moisture content if necessary. In many plants, this step is partially automated, with sensors tracking torque resistance in the mixer to determine when the dough has reached the ideal elasticity. Once mixed, the candy dough is transferred to the extrusion line. This is the stage where Twizzlers take on their famous twisted rope form. The dough is fed into a large extruder, essentially a high-powered screw press that forces the material through a specially designed die. The screw inside the extruder rotates at a controlled speed, kneading and pushing the dough forward while maintaining an even temperature to prevent premature setting. At the end of the barrel, the die features multiple openings shaped to produce the exact cross-section of a Twizzler rope. For the classic variety, the die includes ridged channels that create the candy's spiral grooves. As the dough emerges from the die, it is still warm and soft, making it easy to shape but vulnerable to deformation. To preserve the precise geometry, the extruded ropes immediately enter a cooling conveyor, a long belt that passes through a tunnel where chilled, dehumidified air circulates. This step lowers the candy's temperature and sets the outer surface while maintaining a chewy interior. The speed of the conveyor is carefully calibrated so that cooling is uniform along the rope's entire length. An interesting detail of Twizzlers' production is that the twist in each rope is not solely a result of the die design. The conveyor belt itself may be equipped with rollers that gently rotate the ropes as they move forward, enhancing the spiral effect. The amount of twist is a delicate balance. Too much rotation can weaken the structure and cause breakage, while too little results in a less distinctive look. After cooling, the ropes are ready to be cut to size. Cutting is performed by high-speed guillotine blades or rotary knives synchronized with the conveyor movement to avoid crushing the candy. For standard snack-sized Twizzlers, lengths are typically between 6 and 8 inches, but the same line can be adjusted to produce miniature bites or extra long versions. The cut pieces now move towards the packaging area, but before they are boxed or bagged, they undergo inspection. Quality control technicians pull samples from the line to check twist uniformity, diameter, weight, and surface texture. The moisture content is measured to ensure the candy retains its chewiness during storage. Flavor is also evaluated by trained sensory panels who compare each batch to established taste profiles. Packaging Twizzlers is a study in efficiency. Depending on the product format, they may be wrapped in flexible plastic film, placed in cardboard trays, or sealed in resealable pouches. The packaging machinery begins with an in-feed system that gently aligns the ropes into uniform stacks. These stacks are then transferred into forming tubes where the plastic film is drawn around them, sealed along the edge with heat, and cut into individual packs. Heat seal jaws close the ends to lock in freshness and protect the candy from moisture and oxygen. Lot codes, manufacturing dates, and product identifiers are printed directly onto the packaging by inkjet or thermal printers, ensuring traceability for every unit. Sealed packages are collected onto a takeaway conveyor and then collated into larger cartons for shipping. These cartons are stacked on pallets by robotic palletizers, which arrange the boxes in stable patterns and wrap them in stretch film to secure the load. From here, the pallets are moved to the warehouse, a temperature-controlled environment designed to maintain product quality. Although Twizzlers are relatively stable due to their low moisture and high sugar content, excessive heat can cause surface stickiness or deformation, so storage temperatures are carefully regulated. The finished products are then shipped to distribution centers, retail outlets, and export markets. Behind all of this is a network of automation systems and process controls that keep production running smoothly. Modern Twizzlers plants rely on programmable logic controllers to coordinate mixer cycles, extrusion pressures, conveyor speeds, and packaging rates. These systems integrate with quality control data, enabling operators to adjust parameters in real time if a batch shows signs of deviation from the standard. The flavoring of Twizzlers deserves special mention. While the classic strawberry variety is the most famous, the process allows for a wide range of flavors, from cherry to chocolate to licorice. In each case, the flavor oils are blended into the dough at the mixing stage to ensure even distribution. The choice of flavor affects other parameters as well. For example, chocolate varieties may require a slightly different extrusion temperature due to the fat content in cocoa powder, while licorice varieties may use molasses or anise oil that alter dough handling characteristics. Over the years, Twizzlers production has been refined not only for efficiency, but also for consistency. Early methods required more manual handling, with operators guiding ropes off the extruder and cutting them by hand. Today's operations are highly automated, with minimal direct contact between workers and the product. This not only improves hygiene, but also allows for higher output with fewer defects. Sustainability is becoming a greater focus in candy manufacturing as well. Plants are investing in closed-loop water systems for cooling conveyors, energy-efficient ovens for any heat treatment steps, and waste reduction programs that recycle off-spec candy back into the mix when feasible. Packaging materials are also being evaluated for recyclability, with thinner films and plant-based plastics under consideration. What makes the Twizzlers process so fascinating is the combination of bakery-like dough handling with candy-making sweetness. The extrusion technology is similar to that used in pasta production, yet the ingredients and post-extrusion handling are firmly rooted in confectionery science. It is a hybrid process that demands both mechanical precision and an understanding of how sugars, starches, and fats interact under heat and pressure. When you pick up a pack of Twizzlers, you are holding the result of careful ingredient selection, finely tuned mixing and extrusion, precise cooling and twisting, and airtight packaging. Each rope is the product of countless micro adjustments in speed, temperature, and formulation that ensure the candy's texture, flavor, and appearance are exactly as consumers expect. The story of a Haribo gummy begins with the ingredients, each of which is selected for quality and consistency. At the heart of the recipe is gelatin, a protein derived from collagen that gives the candy its characteristic elastic texture. This gelatin arrives at the factory in dry, granulated form and must be carefully hydrated before use. Alongside gelatin, the formulation includes glucose syrup, often produced from wheat or cornstarch, which provides body, prevents crystallization, and contributes to the chewiness. Sugar is another mainstay, giving sweetness and structural integrity. Additional ingredients include citric acid for tartness, natural and artificial flavorings for each variety, and food-safe colorants to create the rainbow of hues that define Haribo's product line. Every batch of ingredients undergoes rigorous testing in a quality control laboratory before it reaches the main production floor. Gelatin is checked for bloom strength, which determines the firmness of the finished candy. Glucose syrup is tested for solids content and viscosity, ensuring it will flow and set properly in the cooking process. Flavor and color concentrates are measured for potency and compared against established standards. Only when the raw materials pass inspection are they released to the production team. The first major step in making Haribo gummies is the cooking process. This begins in large stainless steel vessels called dissolvers or cooking kettles. Here, sugar, glucose syrup, and water are combined and heated under controlled conditions. The heating process brings the mixture to a high temperature, often in the range of 110 to 140 degrees Celsius, allowing the sugars to dissolve completely and the syrup to thicken. Once the sugar syrup reaches the correct density, pre-soaked gelatin is added. The gelatin is never boiled, as high temperatures would damage its gelling properties. Instead, it is stirred in gently once the syrup has cooled to a safe range, typically between 80 and 90 degrees Celsius. At this point, flavorings, acids, and colors are added. For gummy bears, this might include lemon, orange, raspberry, apple, and strawberry flavor profiles, each paired with a corresponding color. The additives are metered in with precision pumps to ensure every batch is consistent in both taste and appearance. Stirring must be thorough but gentle to avoid incorporating excess air bubbles, which could mar the candy's surface. Once the mixture is fully blended, it is ready to be formed into shapes. This is where Haribo's distinctive starch molding process comes into play. The company uses a method called the Mogul system, an automated production line that allows liquid candy to be deposited into detailed molds with incredible precision. The process begins with large trays filled with a fine, dry cornstarch powder. This starch serves two purposes. It prevents the sticky candy from clinging to the trays, and it helps wick away excess moisture during the setting stage. Each tray passes through a stamping unit where metal dies press the shape of the candy into the starch. Tiny, bare outlines, cola bottle profiles, or whatever form is being produced. The impressions are crisp and exact, ready to receive the warm, liquid mixture. From the cooking kettles, the candy syrup is pumped through heated pipelines to a series of depositor nozzles. These nozzles align perfectly with the starch impressions and release measured amounts of syrup into each cavity. The depositor can switch flavors and colors quickly, allowing for multiple varieties to be produced on the same line with minimal downtime. Once deposited, the trays of liquid candy are conveyed into a long, climate-controlled curing room. Here, they rest for 12 to 72 hours, depending on the recipe, temperature, and humidity. During this time, the gelatin network fully sets, giving the candy its final chewy texture, while the starch continues to absorb surface moisture. The curing rooms are kept at specific humidity levels to prevent the candies from drying out too much or becoming sticky. When curing is complete, the trays move to the demolding stage. The gummy shapes are gently lifted from the starch, which is recovered, dried, and sieved for reuse in future molding. Any excess starch clinging to the candies is removed through a combination of mechanical shaking and soft air jets. The gummies, now fully formed, have a matte appearance and a slightly tacky feel at this stage. To give them the glossy finish consumers recognize, the candies are transferred to large rotating drums called glazing pans. Inside, they are tumbled with a thin coating of food-grade waxes such as carnauba or beeswax, along with oils that enhance shine and prevent sticking. The glazing process is quick but crucial, as it also provides a protective barrier against moisture changes during storage. With their appearance perfected, the gummies proceed to the packaging area. Here, high-speed conveyors feed them into multi-head weighers, machines equipped with multiple hoppers that dispense exact amounts to achieve the target package weight. The candies are dropped into pre-formed bags or into the forming tubes of vertical form-fill-seal machines. These machines create a bag from a continuous roll of printed film. Seal the bottom, fill it with the candy, then seal the top in one continuous motion. For variety packs, sophisticated sorting systems group different gummy shapes and flavors in precise ratios before they reach the weighing step. This ensures that every bag contains the intended assortment. Packaging films are chosen for their barrier properties, keeping the gummies fresh while displaying bright branding. Each bag receives a lot code and best before date for traceability, then passes through metal detection equipment as a final safety measure. The finished bags are gathered into cartons, stacked onto pallets. and wrapped in stretch film to stabilize them for shipping. Pallets are moved to temperature-controlled storage areas until they are loaded onto trucks bound for distribution centers and retailers around the world. Throughout the entire process, quality control remains a constant presence. Samples from each batch are taken at multiple points, from syrup cooking to molding, curing, and packaging, to ensure that every aspect meets Haribo's specifications. Technicians test texture with penetrometers to confirm the perfect chew, measure pH to monitor acidity, and use colorimeters to verify hue accuracy. Flavor panels taste test samples to ensure the product matches established sensory profiles. The production of Haribo gummies has evolved significantly over the decades. Early batches were made by hand in small copper kettles and poured into starch molds one tray at a time. Today's lines can produce hundreds of thousands of pieces per hour, with computerized systems controlling every variable. Yet the core principles remain the same: quality ingredients, precise cooking, careful molding, and patient curing. There is also a growing emphasis on sustainability within Haribo's operations. Many plants now use energy recovery systems to capture heat from cooking processes, recycle starch indefinitely, and source gelatin and sugar from more sustainable supply chains. Efforts to reduce packaging weight and increase recyclability are also underway, ensuring that the joy of gummy bears has a smaller environmental footprint. What makes Haribo's process fascinating is the blend of old-world confectionery craftsmanship and high-tech automation. The mogul molding system, for instance, is an industry standard, yet it still relies on principles that candy makers have used for over a century. The long curing time is a reminder that some aspects of candy making simply cannot be rushed if the desired texture is to be achieved. By the time a bag of Haribo gummies reaches the shelf, it has undergone a transformation from raw sugar, syrup, and gelatin into a perfectly shaped, flavorful, and brightly colored treat. Behind each piece is a network of ingredient sourcing, controlled cooking, precision molding, and patient curing, all supported by layers of quality control and packaging expertise. Lollipop production begins with dry granulated sugar and glucose syrup, delivered in bulk into silos and heated stainless steel storage tanks. The sugar is conveyed through screw feeders into a large dissolving vessel. Simultaneously, glucose syrup is pumped through jacketed pipelines to the same vessel. Water is introduced at a controlled rate to create the initial slurry. The temperature is raised to approximately 110 degrees, while agitators rotate to dissolve all solids. The mixture becomes a clear, homogeneous sugar solution. Once the sugar is fully dissolved, the syrup is transferred via gravity or pump into a vacuum batch cooker or a continuous candy cooker. The cooker raises the syrup's temperature to 145 degrees to 150 degrees, while lowering the internal pressure. The reduced pressure allows water to boil off rapidly without degrading the sugars. The syrup thickens into a dense, high Brix mass. Sensors monitor real-time concentration and adjust heat and vacuum accordingly to maintain the target range, typically 98-99% solids. The cooked candy mass exits the vacuum chamber through a heated outlet, either dropping onto a stainless steel cooling table or into a rotary kneading kettle. On the cooling table, scraper arms fold the mass over itself as it cools. Inside the kettle, mixing paddles rotate at set intervals. The temperature drops gradually to about 90 degree cooks. At this stage, flavor oils, acids, colorants, and emulsifiers are added. Dosing pumps inject precise volumes of ingredients based on the batch weight. Mixing paddles distribute the additives evenly throughout the mass while avoiding air entrapment. If a layered or dual-color lollipop is being produced, the candy batch is divided into separate portions. Each portion is flavored and colored independently in separate kettles. A heating jacket maintains each portion at a stable working temperature. When ready, the portions are loaded into a batch former that can extrude them side by side or swirl them together during the rope formation process. Once mixing is complete, the candy is transferred to a rope sizer. The mass is fed into the machine and drawn through a series of sizing rollers that reduce and elongate the bulk mass into a continuous rope of uniform diameter. Each roller pair incrementally reduces the thickness while maintaining roundness. Servo-driven rollers and load cells ensure tension remains steady along the entire length. Inline cameras monitor the rope diameter within plus 0.5 mm tolerance. As the rope advances, it enters the forming section. Here, it is pulled into a rotary die forming machine. This system consists of 2 steel rollers with precision-cut cavities. As the rope enters the nip point, a stick is inserted from below by a mechanical arm into the soft mass at the exact moment of compression. The die cavities close, shearing the candy rope and forming the lollipop head around the stick simultaneously. Sticks are fed from a vertical hopper onto a horizontal conveyor where they are spaced using star wheels. They travel into the insertion mechanism where grippers or push rods insert them directly into the hot candy as it is formed. The insertion depth, pressure, and angle are all adjustable. Any stick not aligned properly is automatically rejected before contact with the product. After forming, lollipops drop onto a cooling conveyor. The system is divided into zones with progressively lower air temperatures, beginning at around 25 degrees Celsius and dropping to 10 degrees C. Air is circulated through HEPA filters to remove particulates and maintain constant humidity. Cooling takes 5 to 8 minutes, depending on candy size and formulation. The sticks are kept horizontal to prevent gravitational deformation of the still soft candy head. Once fully cooled and hardened, the lollipops enter the wrapping stage. Multiple high-speed wrapping machines operate in parallel. Each machine feeds film from a large roll. Photocells track registration marks to ensure proper logo alignment. Film is cut into pre-sized sheets and fed into the wrapping jaws. Lollipops arrive single file via guide rails and timing screws. As each piece enters the wrapping section, it is met with a film sheet. The candy is centered on the wrapper, and the machine either twist wraps the film at both ends or folds it around the head and seals it with heated jaws and pressure rollers, depending on the wrap style. Speeds reach up to 800 lollipops per minute per machine. Sensors verify the presence of each stick and confirm film seal integrity. If a lollipop is missing a stick, misaligned, or improperly sealed, it is rejected via an air blast or servo diverter. Properly wrapped lollipops are conveyed to a grouping area where they are accumulated for final packaging. Packaging varies depending on format. Some lollipops are bagged in high-speed, vertical form-fill seal machines. The wrapped candies drop into vibratory feeders that portion them into buckets. Buckets empty into a forming tube where plastic film is formed into a bag, filled, and sealed on the top and bottom. Sealing jaws cut and compress the film simultaneously, producing a finished pouch. For tray packs, lollipops are grouped into clusters using a belt divider. Robotic arms or pushers load fixed quantities into cardboard trays or blister packs. Cartoning machines erect the trays, insert the product, and apply hot melt adhesive to seal the cartons shut. Inkjet or laser printers mark each pack with batch codes and expiration dates. Cartons flow to a case packer, where they are grouped and packed into master cartons. Mechanical arms fold the outer box and glue or tape the flaps. These boxes are stacked in layers on pallets by robotic palletizers. The system alternates stack orientation by layer for load stability. Slip sheets are inserted between layers by a vacuum picker. When the pallet is complete, it transfers to a stretch wrapper. A rotating arm or turntable applies a pre-stretched plastic film around the pallet. Wrapping parameters are adjusted based on pallet height, product weight, and load configuration. Once wrapped, each pallet receives a barcode label and is conveyed to the shipping dock. All stages of lollipop production are managed by programmable logic controllers. Every machine, cookers, rope sizers, forming presses, stick inserters, wrappers, and palletizers, is integrated into a plant-wide SCADA system. Operators monitor real-time metrics, including syrup concentration, rope tension, cutter timing, seal temperature, stick depth, wrapping accuracy, packaging speed, and output count. Cooking systems are equipped with conductivity probes and pressure sensors. These devices ensure consistent cooking profiles by regulating steam pressure, vacuum levels, and temperature. Flow meters control syrup and water ratios during dissolving. In the cooling tunnel, temperature and humidity sensors maintain conditions within tight limits to avoid surface cracks or bloom on the hardened candy. Line synchronization is maintained through encoder feedback. Rope feed rate, die rotation, and stick timing are adjusted in real time to prevent drift or misalignment. High-speed cameras inspect each lollipop post-forming for symmetry, stick centering, and surface quality. A quality control logic system tracks defect rates and triggers maintenance if thresholds are exceeded. For striped lollipops, colored candy masses are co-extruded through a color stacking head before entering the rope sizer. Stripes are achieved by arranging differently colored masses side by side or spiraling them with twist control. Layer geometry is controlled by adjusting feed angles and rotation during rope pulling. Dual flavor or filled lollipops use concentric forming. An inner core, often a soft center or powdered flavor pocket, is co-deposited during the forming process. Dual extruders feed the core and shell simultaneously through concentric nozzles. The rope is cut and shaped with the filling encased completely inside. Production speed depends on format. A single forming line can produce over 1,000 lollipops per minute. With multiple lines operating simultaneously, output scales into the millions per day. Each system runs continuously with minimal downtime. Quick release tooling and automated cleaning reduce changeover time between flavors or shapes. Cleaning in place systems are installed on all cooking, mixing, and delivery equipment. These cycles run automatically between batches. Hot water flushes remove residual candy. Caustic detergent circulates through tanks, pumps, and piping. A final rinse ensures all surfaces are food safe. The cleaning process is monitored by conductivity sensors and logged by the control system. Sticks are produced off-site to specification and delivered in bulk. Materials range from extruded polystyrene to compressed paper. Before entering the line, sticks pass through a stick inspector with vision sensors to check for length, roundness, and cleanliness. Only compliant sticks are fed into the press. Any deviation beyond plus 0.5 mm in length or 1 grallis of bend results in rejection. Muffin production in a factory begins with the precision handling of core ingredients: wheat flour, granulated sugar, vegetable oil, eggs or egg replacer, milk or whey solids, water, leavening agents, salt, emulsifiers, and flavor additives. All dry materials arrive in super sacks or silo-fed bulk containers. Liquids are delivered in food-grade tankers and pumped directly into insulated holding tanks. Ingredient feeding systems are automated with load cell-equipped silos, volumetric dosing hoppers, and inline mass flow meters that measure and control exact quantities in real time. The mixing process starts in a large-scale planetary or horizontal mixer. Flour is fed from silos through enclosed pneumatic lines. Sugar is metered in by screw feeders. Liquid components, including water, oils, eggs, and emulsifiers, are introduced from jacketed tanks through pressurized dosing pumps. The mixer uses high-torque arms or paddles to fold the batter, and a PLC-based control system sequences ingredient additions based on a time and speed program. Sensors monitor viscosity, temperature, and mixing torque to determine completion. The mixing cycle is designed to develop a consistent batter texture while minimizing gluten overdevelopment. Most muffins use the muffin method, where liquids and dries are blended quickly with minimal agitation. The final batter is thick, glossy, and aerated. Scraper blades clean the sidewalls of the mixing bowl continuously to ensure uniformity throughout the mix. Once mixing is complete, the batter is pumped into an intermediate holding hopper. These hoppers are jacketed to maintain temperature, typically between 18 degrees Celsius and 26 degrees Celsius, and feature slow-speed agitators to prevent separation. The batter is held under light pressure to feed the depositors efficiently and without introducing excess air. Meanwhile, paper muffin cups are dispensed into baking trays by a cup denister. Trays are made from perforated metal or non-stick coated aluminum, often holding 12 to 24 cavities per tray. The trays travel along a conveyor system toward the depositing zone. As each tray enters the depositor station, it is precisely indexed into place by servo-controlled gates. Batter is deposited using multi-nozzle volumetric piston depositors. These depositors operate with individual cylinders that draw and dispense set volumes of batter into each cup. Fill weights are carefully calibrated, typically between 50 and 120 grams per muffin, depending on product specifications. Tolerances are within +Cs 1.5 grams. Deposit profiles can be circular, spiral, or domed, depending on desired peak structure. Depositor heads are adjustable in height and spacing, allowing format changes without complete tooling replacement. For muffins with inclusions, such as blueberries, chocolate chips, or nuts, an ingredient dosing unit integrates with the depositor. Inclusions are metered into the batter just before deposition to prevent sinking or damage during mixing. The distribution system uses augers or vibration channels to deliver equal portions into each cup, either layered or blended depending on recipe. Optional toppings are applied at this stage. Streusel, sugar crystals, seeds, or flavored crumbles are dropped by overhead sprinklers or belt feeders. These systems are synchronized with tray motion, using vision sensors to detect cup position and deliver toppings directly onto the surface of each batter portion. Filled trays proceed to the oven. Industrial tunnel ovens, either gas-fired or electric, bake muffins continuously. The oven conveyor moves at a speed determined by product size and bake profile, typically yielding a dwell time of 12 to 18 minutes. Oven zones are independently controlled for top and bottom heat, with precise air circulation to ensure even baking. Core product temperature is monitored using inline thermocouples that pierce random samples. Exit temperature targets typically range from 93 degrees Celsius to 98 degrees Celsius. Inside the oven, batter rises due to the activation of chemical leavening agents. Steam forms from the water and egg content, expanding air cells and lifting the batter upward. As proteins coagulate and starches gelatinize, the muffin structure is set. Surface coloration and crust formation are controlled by air humidity and sugar content. Once baked, trays exit the oven onto a cooling conveyor. This conveyor is long enough to allow the muffins to cool from above 90 degrees Celsius down to ambient room temperature, usually within 20 to 30 minutes. High volume air blowers accelerate heat dissipation. Muffins remain in their trays during this time to retain shape and prevent sticking to belts. After cooling, muffins are depanned. A pneumatic or mechanical depanner inverts the tray and applies a brief vacuum or finger push to lift each muffin out. The muffin cups remain intact, and the products are transferred onto a belt for inspection. Empty trays are returned via overhead conveyors or underbelt returns to the cup denesting station for reuse. Muffins are now inspected by a vision system. Cameras mounted above and to the side scan each muffin for volume, surface cracks, peak height, and alignment in the paper cup. Any product that falls outside the specification window is diverted by a mechanical pusher or drop gate. Approved muffins continue to the A packaging zone. Packaging formats vary depending on customer needs. Muffins can be individually wrapped, packed in clamshell trays, or sealed into multi-packs. For individual wrapping, muffins are fed into a flow wrapping line. Each muffin enters a forming collar, where film is wrapped around it and sealed using heated rotary crimpers. Longitudinal and cross seals are made with controlled temperature and pressure. Speeds can reach up to 300 muffins per minute per line. For clamshell packing, muffins are guided into a colada, where robotic pick-and-place arms grip each unit and place it into thermoformed PT trays. These trays are then lidded and sealed with tamper-evident films or snap-on covers. Date and batch codes are printed using thermal inkjet printers. For bulk or food service formats, muffins are loaded into cardboard display trays or placed directly into polyethylene-lined cartons. Cartons are erected from flat blanks using a box erector. Muffins are loaded in rows, either manually assisted or robotically, and the carton is then closed with hot melt adhesive and conveyed toward the palletizer. At the palletizing station, robotic arms equipped with vacuum grippers or mechanical forks stack cartons onto wooden or plastic pallets. Patterns are selected based on case size and distribution route. Slip sheets are inserted every few layers for stability. Finished pallets are stretch wrapped by a rotating arm system and labeled with barcodes and shipping data. All production steps are integrated into a plant-wide control system. Programmable logic controllers coordinate each machine, while SCADA systems provide real-time data on batch progress, line speed, machine temperature, deposit weight, oven humidity, and output count. Operators monitor the entire line from centralized terminals, adjusting set points and diagnosing faults without stopping the process. Ingredient traceability is managed through automated lot tracking. Each ingredient batch is scanned upon entry and linked digitally to every production batch. Finished goods are barcoded and traced back through mixing, depositing, and baking history. If a deviation occurs, the system flags affected pallets and isolates them immediately. Cleaning is performed through a mix of clean in place and clean out of place protocols. Mixing tanks, pipes, depositors, and pump systems are flushed with alkaline detergent followed by a hot water rinse. Baking trays and conveyors are cleaned with steam or dry brushing. Nozzle heads and sensor lenses are wiped with food-safe solvent solutions. Environmental conditions are tightly controlled. The mixing room is temperature stabilized to avoid batter inconsistency. The depositing area uses filtered air to keep particles off open trays. Oven exhaust is captured and scrubbed. Packaging areas are overpressurized with filtered air to minimize dust entry. Air knives and vacuum hoods remove crumbs during transfer points. If muffins are frozen, post-production, they are conveyed directly into a spiral freezer. Cold air at 35 degrees Celsius rapidly reduces product temperature to below 18 degrees Celsius within 30 minutes. Frozen muffins are then flow wrapped or shrink wrapped in bulk, palletized, and moved into cold storage. The entire process is timed to avoid moisture condensation and surface bloom. Shape consistency is enforced at multiple stages. During depositing, laser sensors measure batter height. Post-baking, peak height and crown diameter are scanned optically. Deformed or underfilled units are rejected before reaching packaging. Automated systems collect real-time statistics to maintain statistical process control. The production line is modular. Deposit heads, paper cup sizes, and topping applicators can be changed within minutes. Oven belts, mixing times, and wrap formats are selected through the control interface. Recipe memory allows for instant switchovers without manual recalibration. Muffin factories operate continuously, running multiple shifts with minimal stoppages. High-volume lines produce tens of thousands of muffins per hour. Every unit is created through thermal transformation, timed chemistry, pneumatic forming, and servo-synchronized packaging. Every process step is calibrated, controlled, and monitored to meet exact physical and sensory specifications. The factory production of chocolate chip cookies begins with the bulk delivery of essential raw ingredients. These include wheat flour, white and brown sugars, vegetable shortening or butter substitute, liquid eggs or pasteurized egg products, chocolate chips, leavening agents, salt, emulsifiers, water, and flavorings such as vanilla. Dry ingredients like flour and sugar arrive in super sacks or silo containers and are transferred pneumatically or via screw conveyors into batching silos. Liquid ingredients are stored in temperature-controlled stainless steel tanks connected to dosing lines. Chocolate chips are stored in insulated bins and gently agitated to prevent compaction or melting. Automated ingredient handling systems prepare each batch according to a programmed recipe. The process begins in the scaling room or dosing station, where load cells measure and release precise amounts of dry and wet ingredients into transport hoppers. Materials are conveyed into a high-capacity horizontal mixer, typically of the ribbon or paddle variety. These mixers are equipped with dual-axis blades and variable speed motors. Ingredients are added in a fixed sequence. Fats and sugars first to cream, then eggs and water, followed by dry powders, and finally chocolate chips. Mixing proceeds through defined phases. During the creaming phase, sugar granules break down the fat, creating air pockets essential for cookie spread and tenderness. The incorporation of eggs and water creates an emulsion that stabilizes the dough. As flour and leavening agents are added, the blades slow down to avoid overdevelopment of gluten. The chocolate chips are added last and folded gently to prevent breakage. Inline torque sensors monitor dough consistency, and viscosity meters verify proper development. Batch temperatures are maintained between 18 degrees Celsius and 24 degrees Celsius to prevent fat melt and preserve dough structure. Once mixed, the dough is transferred into a hopper positioned above the forming line. Dough moves via auger or vacuum feed into a volumetric portioning system. A rotary cutter or wire cut depositor divides the dough into individual pieces, each weighing between 25 and 50 grams, depending on the product specification. The depositor uses servo-driven pistons to extrude dough pieces onto a moving steel mesh or Teflon-coated band conveyor. Optical sensors monitor spacing, alignment, and shape, correcting for drift in real time. For wire-cut lines, dough is pushed through nozzles and sliced cleanly by a fast-moving wire as the band advances. For rotary molded formats, dough is pressed into engraved molds on a rotating drum, then released onto the band using a flexible scraper blade. Shape, weight, and chip distribution are confirmed by an overhead vision inspection system using laser profiling and high-speed imaging. Defective pieces are automatically rejected via air puffs or diverter gates. Decorative or functional toppings, such as extra chocolate chips, coarse sugar, or sea salt, can be added before baking. These are applied using vibratory feeders or pneumatic dispensers, synchronized with the conveyor speed. Toppings are placed with positional accuracy, controlled by encoder feedback. The unbaked cookies enter the oven on a continuous conveyor. Most large-scale bakeries use tunnel ovens ranging from 25 to 60 meters in length. Ovens may be gas-fired, electric, or hybrid, and are divided into multiple heating zones. Each zone has independently controlled top and bottom heating elements, recirculating fans, and steam injection systems. Bake times range from 6 to 12 minutes, depending on cookie size, dough moisture, and desired texture. As cookies pass through the oven, heat activates the leavening agents, causing the dough to expand. water turns to steam, fats melt, and proteins begin to coagulate. Sugars caramelize on the surface, contributing to flavor and browning. Top heat ensures color formation, while bottom heat ensures base firmness. An inline thermal imaging system monitors surface temperature and identifies any uneven baking. Oven humidity is also regulated to manage cookie moisture and bite texture. After baking, cookies exit the oven at internal temperatures above 90 degrees and quarks. They are transferred to a multi-tiered cooling conveyor that spans 20 to 40 meters in length. Cool ambient air is blown across the surface of the cookies to gradually reduce their temperature to 30 degrees or lower. The cooling line uses stainless steel or open mesh plastic belts to allow airflow from above and below. Rapid cooling is avoided to prevent cracking or structural collapse. Crumb blowers and air knives remove any loose particles generated during baking. Once cooled, cookies pass through a final inspection station. A high-speed vision system checks each unit for diameter, thickness, browning level, chip exposure, and edge uniformity. Any cookie failing the inspection parameters is ejected automatically. Passing cookies proceed to the packaging section. Depending on the final format, cookies may be packed in flow wrap, trays, clamshells, or flexible pouches. For flow wrap, cookies are aligned single file by a lane guide and transferred onto film. Film is unwound from a roll, cut to length, and wrapped around each cookie. Heat sealing jaws close the ends and form a longitudinal seam. Wrapping speeds can exceed 500 cookies per minute per lane. For tray packing, cookies are collated into rows by a bucket conveyor and placed into pre-formed plastic or paperboard trays by robotic pickers. In multi-pack formats, cookies are stacked vertically or nested side by side using servo-driven stackers. These stacks are inserted into pouches or boxes that are formed, filled, and sealed in a continuous motion machine. Machines apply nitrogen flush to pouches before sealing to displace oxygen and extend shelf life. Date codes and batch numbers are applied using thermal inkjet printers or laser coders. Barcodes are printed for inventory and traceability. Wrapped products are collated into cartons by robotic arms equipped with suction grippers. Cartons are sealed with hot melt glue and stacked onto pallets in pre-programmed patterns. Palletizers use multi-axis robots with slip sheet dispensers to build stable, shippable loads. Pallets are conveyed to a stretch wrapper where they are secured with plastic film. Labels with tracking codes and distribution information are applied before pallets are moved to dispatch or cold storage. All stages of production are monitored and controlled by a centralized PLC-based automation system. The entire factory line is integrated through SCADA interfaces that provide operators with real-time dashboards showing mixer status, dough temperature, line speed, oven zone profiles, moisture content, wrapping rate, and defect counts. Recipe management software ensures every batch conforms to specification and every change is logged digitally. Clean-in-place systems are used for all dough contact equipment. After production, mixers, hoppers, pipelines, and depositors are flushed with food-safe detergent and rinsed with hot water. Belt surfaces are cleaned with steam or sanitizing solution and scraped with mechanical blades. Oven interiors are brushed and vacuumed between shifts to remove carbonized residue. Environmental conditions like air pressure, temperature, and humidity are tightly controlled in all processing zones to prevent microbial growth and maintain dough stability. Ingredient traceability is maintained through barcode scanning and batch logging. Each input is recorded upon arrival and linked to its corresponding finished batch. If any quality issue is detected downstream, affected products can be isolated immediately through backtracking. Quality assurance teams conduct routine sampling, including water activity, texture, chip dispersion, packaging seal integrity, and shelf life simulations in controlled chambers. Some facilities operate in robing lines for chocolate-dipped or striped cookies. These cookies exit the oven and are passed through a tempering tunnel where they receive a coating of milk, dark, or white chocolate. The coating is applied using cascading curtains or rotating drums, followed by a cooling tunnel with airflow designed to produce a glossy finish and stable crystallization. Other variants include filled cookies, where dough is extruded with a central cavity filled with chocolate paste, caramel, or fruit gel. These are formed using a co-extrusion head that aligns both dough and filling. The filled ropes are cut by guillotine or rotary blades and shaped prior to baking. Additional vision inspection ensures filling is centered and not leaking. The process for Snickers peanut butter begins with the receipt and inspection of raw materials, including roasted peanuts, refined sugar, corn syrup, dextrose, hydrogenated vegetable oil, skimmed milk solids, cocoa liquor, cocoa butter, soy lecithin, salt, egg white solids, lactose, whey, and artificial flavors. Each ingredient is stored in designated silos or temperature-controlled containers depending on its physical state. Dry powders are handled in gravity-fed bins, while oils and syrups are stored in jacketed tanks with agitation and temperature control to maintain fluidity. Peanuts used in the formulation are first screened for foreign matter using rotary sieves and magnetic separators, then conveyed into buffer hoppers feeding a roller mill that cracks them into uniform granules. The granulated peanuts are then pneumatically transferred to storage silos for batch-based dispensing into the peanut butter blend. The peanut butter layer is produced in a batch mixing system where peanut granules are combined with vegetable oil, sugar, salt, and stabilizers in a ribbon blender with temperature regulation. The mixture is homogenized using a high-shear inline mixer and heated to 48 tart 52°C to achieve pumpable viscosity. The finished peanut butter is stored in jacketed holding tanks equipped with level sensors and recirculation loops to prevent phase separation. The nougat layer is prepared using a continuous aeration system. Corn syrup, sugar, and water are cooked in a steam-jacketed vessel to 120 degrees and transferred to an aerator, where air is whipped into the syrup along with milk solids, egg white solids, and stabilizers. The result is a light, aerated nougat with controlled density between 0.35 and 0.45 GC/Sec-Gem3. The nougat is extruded through a calibrated nozzle system onto a continuously moving cooling belt lined with a polyethylene release film. The nougat band is cooled to below 20 degrees Celsius using overhead chillers and bottom surface cold plates. Once cooled, a uniform layer of peanut butter is deposited onto the surface using a curtain depositor. The thickness of this layer is maintained using servo-controlled doctor blades. Viscosity and temperature of the peanut butter are constantly monitored by inline viscometers and thermocouples, with feedback loops adjusting jacket temperature and pump speed. A caramel layer is prepared by cooking sugar, glucose syrup, milk solids, and fats to a target temperature of 115 or 118 degrees, followed by emulsification in a vacuum mixer to remove air bubbles. The caramel is applied as a third layer over the peanut butter using a heated roller spreader system with a calibrated gap to ensure uniform layer thickness. The caramel is cooled rapidly using forced air and chilled roller contact to reach slicing firmness. The tri-layer slab, consisting of nougat, peanut butter, and caramel, is conveyed through a compaction system consisting of top and bottom pressure belts to eliminate internal air pockets and ensure structural uniformity. The slab then enters the slitter station, where rotary knives cut it longitudinally into lanes matching the final bar width. Each blade is aligned using digital edge sensors to maintain cutting accuracy within plus or 0.5 millimeters. The individual lanes are separated using diverging conveyors and conveyed into the guillotine cutter. where servo-driven blades slice the moving slab into individual bar lengths, typically 38 to 52 grams per unit. Cut bars are spaced automatically using smart belts that adjust speed based on line accumulation to prevent product overlap and damage. Any misshaped or undersized bars are rejected using pneumatic knockoff arms. Bars proceed to the enrobing station, where they pass under a waterfall curtain of tempered milk chocolate. The chocolate is maintained at 30 Rs and has a viscosity range of 1,800 to 2,200 centipoise. A vibrating wire mesh belt ensures uniform base coverage, while an air knife blows off excess chocolate from the top and sides. Enrobed bars are passed through a vibrating section to settle the coating and remove trapped air. The enrobed bars enter a cooling tunnel divided into progressive zones starting at 10 degrees C and gradually increasing to 16 degrees C to prevent fat bloom and cracking. Tunnel length is approximately 30 to 40 meters, with dwell time ranging from 5 to 8 minutes depending on coating thickness and line speed. Product core and coating surface temperatures are measured at tunnel exit to confirm stabilization below 20 degrees. Post-cooling, bars are inspected using machine vision systems that assess enrobing quality, dimensional conformity, and surface defects such as bubbles or incomplete coverage. Rejected units are logged by defect type and removed automatically. Accepted bars continue to the packaging line, where they are fed into a flow wrapper via vibratory lanes and pocket conveyors that align them to wrapping speed. Wrapping film is fed from a roll and registered using optical mark sensors. The film is formed into a tube around each bar using a forming box. Longitudinal seams are sealed by rotary heat seal wheels, and end seals are created by jaw sealers operating at 135-150 degrees Celsius. Barcodes and date codes are printed in line using thermal transfer printers. Film tension, seal temperature, and print registration are continuously monitored by the wrapper PLC. Wrapped bars are weighed using in-motion check weighers with a resolution of 0.1 grams. Any bars outside the wire tolerance band are ejected using pneumatic side gates. Accepted bars are collated into groups by rotary collators and packed into folding cartons by robotic pick-and-place systems using vacuum cups. Cartons are erected, filled, and sealed with hot melt adhesive applied by contact nozzles. Cartons are verified by weight and barcode before being conveyed to case packing. Case packing involves grouping cartons into shipping cases that are erected and sealed by automated case erectors and tapers. Cases are labeled using thermal inkjet or print and apply labelers and stacked onto pallets using robotic arms with end effectors configured for the case size. Pallets are wrapped with stretch film and labeled with pallet license plates that include batch number, product code, production line, and timestamp. Finished pallets are stored in temperature-controlled warehousing environments between 18-20 C2 degrees and 50-60% RH. Warehouse management systems, WMS, use barcode scanning to log pallet locations and ensure FIFO inventory management. Distribution occurs through cold chain logistics to ensure product quality during transportation. Each process step is monitored and controlled using a supervisory control and data acquisition SCADA system that collects data from sensors, scales, thermocouples, and flow meters across all stages. This data is displayed on human-machine interfaces, HMIs, for line operators and stored in batch records for traceability. Any deviation from standard parameters triggers alarms and corrective actions. Allergen segregation protocols are enforced at every stage. Peanut and milk processing areas are physically segregated. Equipment used for peanut butter and chocolate are color-coded and cleaned separately. Swab testing for protein residues is conducted after cleaning and before changeovers. Cleaning validation includes visual inspection, chemical residue tests, and microbial swabbing. Preventive maintenance schedules for all equipment are based on run hours or production cycles. Components such as chocolate pumps, depositor nozzles, cutter blades, belt rollers, and sealing jaws are inspected and replaced as needed. Maintenance activities are logged in a computerized maintenance management system, CMMS, which alerts engineering teams when parts reach predefined wear thresholds. Quality control includes hourly sampling of bars for destructive testing. Tests include measurement of bar weight, length, width, height, chocolate shell thickness, peanut distribution, and filling ratio. Moisture content is tested using rapid moisture analyzers, while texture is measured using texture profile analysis, TPA, machines. Sensory testing is performed by trained panelists in isolated booths with controlled lighting and ventilation. Shelf life studies are conducted by storing finished products under accelerated and ambient conditions. Parameters tested include moisture migration, lipid oxidation, microbial stability, chocolate bloom, and filling separation. Results are used to validate expiration dates printed on each unit. Finished goods are subject to audit by internal QA and external certification bodies to ensure compliance with food safety standards. All production, inspection, and packaging records are stored electronically and can be retrieved instantly for traceability. Raw material lot numbers are linked to final product batch codes, allowing for upstream and downstream tracking in case of complaints or recalls. Root cause analysis is performed for any non-conformance, with results reviewed in monthly quality audits. M&M's caramel candies are manufactured through a multi-stage process that includes caramel cooking and forming, caramel center pre-coating, chocolate panning, hard shell sugar coating, polishing, sorting, inspection, and packaging. Each of these stages is optimized for continuous production and strict dimensional and weight tolerances. The process begins with preparation of the caramel center using industrial cooking vessels equipped with direct steam injection and mechanical agitation. A mixture of glucose syrup, refined white sugar, sweetened condensed milk, palm oil, emulsifiers, salt, and natural flavoring is pumped into the batch cooker. The initial ingredients are metered by mass flow meters and load cells to ensure precise ratio control, typically with a solids concentration exceeding 85% in the final cooked mass. Cooking is conducted at temperatures between 115 degrees Celsius and 120 degrees Celsius, and continuous agitation prevents scorching and ensures homogeneous heating. A vacuum step may be applied after atmospheric cooking to reduce moisture content without exceeding target temperatures, improving chew texture and shelf stability. Once the required consistency is reached, the caramel is transferred to a cooling table or cooling drum equipped with scraper arms, which reduce the mass temperature to below 50 degrees Celsius and prepare it for forming. The cooled caramel mass is sheeted and cut using a rotary cutter and high-precision die system. The sheeted caramel slab is passed through gauge rollers to reduce thickness and fed into a rotary die-cutting unit where small square or rectangular cores are punched out. The cutting system operates in synchronized alignment with the conveyor speed to avoid misshaping. Each core is formed to within +T 0.2 mm of the target dimensions, and cut weights are maintained at 2 to 3 grams per center depending on final candy size. After cutting, the caramel centers are conveyed to a pre-coating drum where they are tumbled with a fine mist of modified starch or food-grade wax. This stage prevents sticking and prepares the surface for chocolate adhesion. The pre-coated caramel pieces are temporarily stored in stainless steel bins under humidity-controlled conditions with less than 40% RH before being transferred to the chocolate panning units. Chocolate coating is conducted in automated panning drums with oscillating movement and programmable dosing cycles. Each pan receives a calibrated quantity of caramel centers and begins rotation at 18 to 24 RPM. Tempered milk chocolate is sprayed onto the tumbling centers in controlled quantities through heated nozzles. Each chocolate application is followed by a cooling phase using dehumidified cold air injection to solidify the layer before the next application. This chocolate build-up cycle continues for multiple iterations until the centers reach the specified chocolate layer thickness. Sensors within the panning unit monitor temperature, humidity, and drum load to prevent agglomeration or flattening. The total chocolate coating phase typically lasts 60 to 90 minutes, depending on desired shell thickness and line speed. By the end of this stage, each center is fully encapsulated in chocolate and cooled to under 25 degrees Celsius before proceeding to the sugar coating line. Sugar coating, or hard panning, is performed in high-capacity rotating pans with batch sizes ranging from 300 to 600 kilograms. A mixture of sucrose, glucose syrup, water, colorant, and titanium dioxide is sprayed in layers onto the chocolate-coated centers. The initial applications are made with higher syrup content to ensure adhesion and are followed by increasingly dry applications to harden the shell. Between each application, cold air is blown into the pan to crystallize the syrup and lock the layer in place. The coating is built in 20 to 40 layers, with rotation speed, syrup flow rate, and airflow rate adjusted in real time by PLC-controlled systems. Specific gravimetric dosing pumps ensure each batch receives a uniform mass of syrup and colorant. Standard M&M's caramel products are colored using a fixed ratio of FDA-approved colorants, with pan scheduling arranged to avoid cross-color contamination. Each color batch is tracked with a unique identifier linked to its dye lot and pan ID. As the sugar shell builds, the product passes through a smoothing phase where the surface is hydrated and then gently polished with microcrystalline wax. This polishing provides the final product with its gloss and protective coating. A final tumbling phase is conducted in pans lined with polishing baffles and anti-static systems to prevent buildup on the interior walls and ensure free movement of the candies. After polishing, M&M's caramel units are conveyed to the grading station. A multi-tiered vibratory grading system separates any units that deviate from size specifications. Grading is followed by weight sorting, using high-speed check weighers capable of scanning up to 300 units per minute. Acceptable candies fall within a defined weight range. Over- and underweight items are automatically rejected and logged by defect code. Product inspection follows. Each candy passes through a vision system using a series of high-resolution cameras and 360-degree rotation to check for shell defects, discoloration, incorrect sizing, and incomplete polish. Any non-compliant unit is removed from there, streamed via pneumatic nozzles, and collected in segregated bins. Rejected items are logged and analyzed for trends in production issues, triggering upstream corrective actions if thresholds are exceeded. Accepted product is conveyed to the packaging system, where candies are temporarily stored in surge hoppers with level sensors to buffer production flow. Product is dosed using multi-head combination weighers that calculate the optimal combination of candies to achieve target package weights, typically 34 to 80 grams, depending on SKU. Weigher buckets are constructed of low-friction stainless steel and cleaned regularly to prevent flavor, carryover, or build-up. Filled product drops into vertical form-fill seal machines, where printed laminate film is formed into a pouch, filled, and sealed with constant heat seal bars. Seal integrity is verified using pressure sensors and thermographic imaging. A nitrogen flush is applied before sealing to reduce oxygen levels inside the pouch, thereby enhancing shelf life. Packages are printed with production code, best by date, line number, and timestamp using continuous inkjet printers. Sealed pouches are conveyed to check weighers for final weight verification, and then pass through metal detectors set to detect ferrous, non-ferrous, and stainless steel contaminants. Any off-weight or contaminated package is rejected. Accepted packages are collated into larger trays or cartons using pick-and-place robotic arms equipped with vacuum grippers. Cartons are assembled, filled, and sealed using hot melt adhesive and barcode labels applied on the side panel. Shipping cartons are scanned and aggregated onto pallets using automatic palletizers that form specific stacking patterns for warehouse efficiency. Each pallet is wrapped with stretch film and labeled with pallet-level tracking codes tied to the plant's manufacturing execution system. Pallets are transferred to a finished goods warehouse where temperature is maintained at 18 to 20 Celsius and humidity is kept under 60% RH to protect product quality. Quality assurance sampling occurs every 15 to 30 minutes at critical control points. Samples are taken from post-coating, post-polishing, and final package stages. Laboratory tests include moisture analysis via halogen, moisture analyzers, shell thickness measurement with micrometers, coating adhesion tests, drop impact testing for shell integrity, and taste panel validation. Shelf life studies are conducted on retained samples stored at standard and accelerated aging conditions. Cleaning and sanitization are conducted on a rotating schedule. Chocolate and caramel handling areas undergo full CIP clean-in-place procedures involving hot alkaline solutions, acid rinses, and sterile water flushes. Sugar panning and polishing pans are dry cleaned using brushes, vacuum systems, and compressed air. Contact surfaces are swabbed for microbial residues, and test results are logged digitally for traceability. Allergen control is strictly enforced. Caramel and chocolate processes containing dairy and soy are segregated. Line clearance protocols require full removal of previous ingredients, verified by visual inspection and protein swab testing before new production begins. Changeovers are validated with QA sign-off. Batch tracking is implemented through digital batch records containing ingredient lots, process parameters, equipment settings, cleaning records, operator IDs, inspection results, and deviation logs. Any deviation from specification limits requires root cause analysis and corrective action under documented quality systems. Rework from rejected product is limited and processed only after evaluation of safety and quality impact. Preventive maintenance occurs based on machine runtime hours. Key systems like chocolate pumps, coating nozzles, panning motors, weighing buckets, and forming jaws are monitored for wear and replaced proactively. Predictive diagnostics include vibration analysis and temperature monitoring of motor bearings, and these readings are stored in a central database for long-term equipment performance tracking. The production of Twix White begins with the synchronized preparation of three main structural components: the shortbread biscuit base, the caramel layer, and the white chocolate coating. Each component is manufactured in separate sublines within the facility and converges later during the bar forming phase. The process starts with the biscuit base. Refined wheat flour, invert sugar syrup, vegetable shortening, powdered milk, salt, and leavening agents are dispensed into a horizontal planetary mixer. Dry ingredients are fed from bulk storage silos through gravity chutes or pneumatic lines, each portion controlled by weigh batches to an accuracy of plus watt boige 1%. Liquid components are pumped from heated jacketed tanks and injected through metered valves. The mixing cycle includes two stages: dry blending for even distribution of powders, followed by wet incorporation using medium speed agitation. The dough is formed to a target moisture content between 16 to 18% to ensure optimal flow and shaping characteristics. Upon completion, the dough is conveyed via a stainless steel auger system to a rotary molder. In the rotary molding station, The dough is formed into uniform, rectangular shortbread fingers. The molder consists of a rotating drum engraved with bar-shaped cavities and a compression roller. Dough is pressed into these cavities as the drum rotates over a steel forming plate. Excess dough is scraped off by a doctor blade and recirculated back into the feed system. The molded dough pieces drop onto a perforated baking belt made of food-grade stainless steel mesh. The formed biscuit bases enter a continuous tunnel oven with multiple heating zones. Each zone uses indirect gas-fired heat or electric radiant panels to maintain a gradient from 180 degrees Celsius at the entrance to 220 degrees Celsius in the final zones. The baking time ranges between 8 to 10 minutes. Infrared sensors monitor surface temperatures, while dew point sensors control internal humidity. The goal is to fully gelatinize the starch, set the structure, and reduce internal moisture content to below 3.5%. After baking, the biscuits are transferred to a mesh cooling conveyor where ambient air is forced from both above and below using axial fans. Surface temperature is reduced to under 30 degrees before the biscuits are sent downstream. During this phase, any misshaped or cracked bases are automatically rejected using laser sensors and high-speed diverters. Parallel to biscuit preparation, caramel is cooked in a steam-jacketed stainless steel cooker equipped with a vacuum system. The caramel mixture consists of glucose syrup, refined sugar, sweetened condensed milk, vegetable fat, and emulsifiers. The blend is heated to between 115 degrees Celsius and 120 degrees Celsius under continuous agitation to achieve a homogeneous, smooth consistency. A vacuum stage follows to reduce moisture content and prevent Maillard browning beyond the desired level. Once cooked, the caramel is pumped through an inline cooler, reducing its temperature to 50 to 55 degrees Celsius and fed into a pressurized buffer tank. The caramel is held under constant agitation to prevent crystallization and separation. It is then transferred to a curtain depositor located above the biscuit lines. Each biscuit base moves underneath the depositor at synchronized speeds, where a layer of caramel approximately 3 to 5 mm thick is dispensed onto the center. The caramel-coated biscuits proceed to the chilling tunnel, which operates between 5 degrees Celsius and 8 degrees Celsius, with controlled air velocity and laminar flow. This section ensures the caramel firms to a semi-solid state, allowing the bars to retain shape during subsequent handling. Cooling dwell time is carefully controlled to prevent cracking or internal condensation. Next is the enrobing process. White chocolate coating is prepared by melting white compound chocolate composed of sugar, milk solids, cocoa butter alternatives, and lecithin. It is stored in heated tanks, maintained at 42-45 degrees Celsius. The chocolate is filtered to remove particulate matter and pumped into the enrober. Each caramel-topped biscuit is conveyed through a waterfall curtain of white chocolate. The enrober consists of a chocolate pump, curtain plate, bottoming pan, and vibrating removal section. The base of each bar contacts a submersion roller to ensure full underside coverage. A vibrating wire belt helps distribute the chocolate evenly, while an air knife system positioned immediately after the curtain blows excess chocolate off the top and sides to maintain uniform shell thickness. The enrobed bars enter a cooling tunnel set to 10 to 14 degrees. The tunnel is 20 to 30 meters long and provides 3 and 6 minutes of cooling time. The goal is to solidify the chocolate coating to a firm, glossy finish without causing thermal shock or shell fractures. Airflow patterns and tunnel humidity are tightly regulated to prevent surface bloom and condensation. Upon exit, bars pass through a vision inspection system. High-resolution cameras capture top, side, and bottom views. Pattern recognition software detects coating voids, caramel leaks, surface cracks, and dimensional anomalies. Bars not conforming to target specifications are removed via pneumatically controlled ejectors and collected in reject bins for offline evaluation. Compliant bars are transferred to the primary packaging line. Bars are individually flow wrapped using printed multi-layer laminate films. The film is drawn over a forming collar and sealed using horizontal sealing jaws operating at 135-145 degrees C. Before the end seal is applied, a nitrogen flush displaces oxygen within the wrapper to preserve product freshness and extend shelf life. A thermal inkjet printer marks each wrapper with a date code, lot number, and timestamp synchronized with the manufacturing execution system. Sealed bars are conveyed through metal detectors calibrated for stainless steel and ferrous particles at sensitivities below 1.5 ppm. Packages outside weight or contaminant parameters are ejected and logged. Wrapped units are collected into collators that form groups for secondary packaging. Robotic pick-and-place systems use vacuum grippers to load bars into pre-formed cartons or trays. Cartons are closed using hot melt glue, and barcodes are printed for traceability. Completed cartons are conveyed to automated case packers. Shipping cases are assembled, filled, and sealed using tape or adhesive. Each case is labeled with a shipping code, pallet code, and production metadata. Palletizing robots stack cases according to predefined patterns. Pallets are stretch wrapped and scanned before being stored in the finished goods warehouse, which maintains ambient temperatures of 18 to 20 degrees and relative humidity under 60%. Each bar produced is tied to a batch number through digital production records, including all ingredient lot numbers, mixing parameters, baking temperatures, caramel cooking data, enrobing flow rates, cooling dwell times, and packaging specifications. These records are accessible for traceability, audits, and regulatory compliance. Routine inline quality control includes sampling from every production hour. Samples are weighed, measured, and evaluated for coating thickness, layer adhesion, caramel placement, and hardness using calibrated micrometers and texture analyzers. Moisture content is verified using halogen moisture balancers, and chocolate temper is tested with temper meters to confirm crystallization profiles. Laboratory testing also includes water activity analysis, fat bloom resistance, and accelerated shelf life testing under elevated temperature and humidity conditions. Results are logged in a quality database and reviewed by technical managers during shift changes and weekly audits. Sanitation of the line is scheduled daily and weekly depending on the zone. Dry cleaning is applied to the biscuit molding and baking lines using brushes and compressed air. Wet cleaning is used on caramel and chocolate zones, involving hot water rinses, food-safe alkaline detergents, acid neutralizers, and sanitizer sprays. Enrober parts are disassembled and cleaned using CIP-compatible tanks. Allergen management involves physical segregation of peanut, tree nut, and dairy-containing ingredients. Changeovers require full clean-out of product contact surfaces and verification using allergen-specific protein swab kits. If protein residue exceeds defined thresholds, equipment is re-cleaned until test values fall within limits. All material movement, from raw ingredient delivery to palletized product dispatch, is tracked using barcodes and integrated into the facility's ERP and SCADA systems. These systems enable real-time monitoring of production rates, downtime, line efficiency, scrap rates, and output per shift. Alarm logs, deviation reports, and maintenance requests are automatically archived for compliance purposes. Preventive maintenance schedules cover all rotating equipment, pumps, cooling compressors, depositor heads, vibratory conveyors, belt motors, and sealing modules. Wear parts such as blades, nozzles, bearings, belts, and gaskets are replaced at specified run-hour intervals. Predictive analytics using vibration sensors and thermal imaging assist in identifying failure risks before downtime occurs. The manufacturing process of Kinder Bueno begins with the preparation of the wafer batter. The primary ingredients, wheat flour, water, vegetable oil, lecithin, and leavening agents, are fed from storage silos and tanks into a stainless steel batching system. Each component is dosed with gravimetric precision, and the batch is mixed in a jacketed high-shear mixer. The flour is delivered via screw conveyors, water is flow-metered, and emulsifiers are introduced through liquid dosing pumps. Mixing time, rotation speed, and temperature are regulated to ensure that the batter reaches a uniform consistency suitable for rotary plate baking. Viscosity is continuously measured during mixing to maintain the desired flow behavior. The mixed batter is transferred to the baking system via diaphragm pumps. A rotary oven equipped with a sequence of upper and lower metal baking plates receives the batter through a synchronized volumetric depositor. The baking plates close, forming a mold that defines the half-shell structure of the wafer casing. The plates travel through the baking chamber, where they are heated via direct flame or electric elements. Internal plate temperature is maintained between 160 degrees Celsius and 180 degrees Celsius, with each shell requiring approximately 90 seconds of exposure to solidify and develop structural integrity. As the mold progresses through the oven, moisture is evaporated, and a thin, crisp wafer forms along the contours of the mold cavity. Upon completion of the baking cycle, the plates open automatically. Mechanical lifters remove the wafer shells and place them onto a wire mesh conveyor. The shells are cooled using forced ambient air delivered through adjustable nozzles positioned above and below the conveyor. The shells then enter a trimming station, where a high-speed rotating blade removes excess material from the shell edges to ensure uniform shape and dimension. The trimmed shells are rotated and aligned into uniform orientation using guide rails and belt positioners. The output is arranged into index stacks for timed transfer to the filling system. The hazelnut cream filling is produced on a separate line. Whole hazelnuts are delivered in bulk and transferred into a vibratory screening unit that removes any residual shell fragments or extraneous material. The screened nuts are routed through a mechanical conveyor to a continuous roasting system. Roasting is carried out in a rotating drum oven or a belt-type hot air roaster. The roasting temperature is controlled at 150 degrees Celsius to 160 degrees Celsius, with exposure times ranging from 20 to 25 minutes depending on kernel size. Roasted hazelnuts are cooled rapidly using counterflow ambient air to prevent oil migration. Blanching follows, using mechanical abrasion rollers to remove the skin. Blanched nuts are transported directly to the grinding section. Hazelnut grinding is conducted in 2 stages. The first stage uses a hammer mill or pin mill to reduce particle size to below 200 microns. The ground nut mass is then passed through a ball mill where particle size is further reduced to below 30 microns. The resulting hazelnut paste is transferred to a mixing tank equipped with counter-rotating blades. To this paste, specific quantities of refined sugar, vegetable fat, milk powder, and lecithin are added. The blend is agitated at a controlled temperature, generally between 35 degrees Celsius and 40 degrees Celsius, to produce a homogeneous, spreadable cream. Once fully emulsified, the hazelnut cream is transferred to buffer tanks maintained at a consistent temperature and mixed gently with slow-speed impellers to preserve structure. Wafer shells are filled using a precision depositor that aligns with each open wafer cavity. The hazelnut cream is pumped through heated stainless steel lines and dispensed in measured volumes through multiple nozzles. The depositor operates in cycles synchronized with the conveyor to allow for accurate deposit into each cavity. Each half shell receives a center-aligned column of cream filling, stopping short of the rim to accommodate sealing with the upper half shell. After deposition, the second wafer half is picked and placed onto the filled shell using robotic vacuum grippers. Sealing of the wafer is carried out with a dual pressure belt system that presses both halves together at controlled force. The sealed wafer unit is transferred to the next processing stage, where the internal coating is applied. A tempered chocolate mixture is circulated through a closed-loop system and delivered to the coating station. Each sealed bar passes beneath a chocolate curtain that applies a uniform internal chocolate layer around the wafer structure. An excess removal mechanism uses vibration and compressed air knives to prevent pooling or uneven distribution. The coated units then enter a cooling tunnel, which uses recirculated chilled air to bring the chocolate to a solid state without thermal shock. Tunnel dwell time is determined by belt speed and tunnel length, ensuring full crystallization of the chocolate layer. After internal cooling, bars are conveyed to the external enrobing line. This section applies the milk chocolate outer coating. The coating chocolate is prepared in advance by melting, tempering, and circulating through jacketed pipes maintained at 30 degrees Celsius to 32 degrees Celsius. The bars pass over a mesh belt conveyor under an overflow system, where chocolate is applied to the top, sides, and bottom simultaneously. The base layer is achieved through contact with a rotating chocolate-coated roller positioned beneath the belt. Excess chocolate is removed using oscillating air jets and a vibrating belt section. Once the milk chocolate layer is set, decorative stripes of dark chocolate are applied. A multi-head depositor positioned above the belt releases thin lines of dark chocolate in a controlled motion pattern, creating the characteristic curved stripe design. The application of stripes is synchronized with belt movement, and chocolate flow rate is controlled using peristaltic pumps and pressure regulators. The decorated bars are sent through a secondary cooling tunnel. This unit is divided into multiple temperature zones, gradually reducing the product temperature to ensure final structure without bloom or surface defects. After exiting the second cooling tunnel, the finished bars are individually wrapped using horizontal flow wrapping machines. Each bar is conveyed into a forming box where the wrapper film is folded around the product and sealed longitudinally by heated rollers. End seals are created using rotating sealing jaws that compress and heat seal the film ends. The temperature, jaw pressure, and dwell time are adjustable parameters based on film type and bar temperature. The wrapping material is pre-printed with branding and is fed from reels under tension-controlled rollers. Wrapped bars are grouped by rotary collectors and transferred to the bar collation unit. This unit counts bars and arranges them for packaging into twin packs or other desired formats. Grouped units are transferred into pre-formed secondary sleeves or cartons. These are closed with mechanical tucks or glue application systems, depending on the product configuration. The fully assembled and sealed cartons are discharged from the line at regular intervals. At no point during the process are the components exposed to cross-contamination, as each line is physically separated and supplied with dedicated material flow and thermal systems. The entire production line is configured to operate in continuous motion, with conveyors, deposition units, coating systems, and cooling tunnels fully synchronized. All components, from batter mixing to final wrapping, are connected through an uninterrupted mechanical chain, resulting in fully assembled, filled, coated, and wrapped Kinder Bueno units. Production of Bounty begins with the formation of the coconut filling. The core ingredient, desiccated coconut, arrives in bulk and is stored in sealed silos or stainless steel containers. The coconut is unloaded via vacuum conveyors into pre-cleaning units, where it passes through a series of vibratory sieves and magnetic separators to remove oversized flakes, fine powder, and metal fragments. After initial screening, it enters holding hoppers equipped with agitation paddles to prevent bridging during downstream feeding. From the hoppers, desiccated coconut is metered into large-scale batch mixers. In parallel, a blend of glucose syrup, invert sugar, and emulsified fats is prepared. Glucose syrup is stored in heated bulk tanks and is circulated through jacketed piping systems to maintain flow at a consistent temperature between 45 degrees Celsius and 60 degrees Celsius. The syrup is pumped into dosing vessels, where flow rate is precisely controlled via mass flow meters. Invert sugar, used for moisture retention, is added next. Solid fats, typically palm kernel or coconut oil, are stored in insulated tanks, liquefied by indirect heating, and pumped through a closed-loop recirculation system to maintain fluid consistency. The syrup-fat mixture is introduced into the batch mixer with the desiccated coconut. The mixer, usually a double Z paddle or ribbon blender, operates at low to medium shear to avoid breaking the coconut structure while ensuring even distribution of binders. The mixing chamber is jacketed to maintain the blend at 40 degrees Celsius to 45 degrees Celsius, aiding uniform fat dispersion. Mixing duration is controlled by programmable logic controllers and typically runs for 8-12 minutes per batch, depending on volume. Load cells beneath the mixer verify batch mass consistency. The completed coconut mixture is discharged through a pneumatically controlled gate valve onto a spreading conveyor. This conveyor leads to a slab, former consisting of a series of compaction rollers and edge formers. The mixture is shaped into a continuous ribbon or slab of fixed width and height. A top-leveling blade smooths the surface, and lateral guides maintain slab width, typically between 100 mm and 150 mm. Roller pressure and conveyor speed are adjusted to control slab density and moisture distribution. The continuous slab moves into a cooling tunnel to solidify the matrix prior to cutting. The tunnel uses chilled air circulated by variable speed blowers. Tunnel length ranges from 15 to 25 meters depending on line throughput, and internal temperature is maintained between 5 degrees Celsius and 10 degrees Celsius. Dwell time in the tunnel is approximately 3-5 minutes, enough to reduce the slab surface temperature to below 15 degrees Celsius. Exiting the cooling tunnel, the solidified slab is conveyed towards the portioning system. It first encounters a longitudinal cutting unit consisting of rotary disc blades that slice the slab into multiple parallel lanes. Blade spacing is adjustable based on final product width. These lanes proceed to the transverse cutting station equipped with servo-controlled guillotine knives. Blade actuation is synchronized with conveyor speed to ensure precise cut length, generally between 55 mm and 65 mm per piece. Each resulting rectangular coconut core is now a preform ready for enrobing. These preforms are transferred via a servo-driven indexing conveyor onto a perforated steel mesh belt leading into the enrobing section. In the enrober, the preforms pass beneath a tempered milk chocolate curtain. The chocolate, maintained at 30 degrees Celsius to 32 degrees Celsius, is pumped from a holding tank that continuously circulates it through a tempering unit. The tempering process cycles the chocolate through heating, cooling, and reheating, producing a stable beta crystal structure for gloss and snap. As the coconut bars pass beneath the chocolate curtain, they receive full top and side coverage. Simultaneously, a bottoming roller applies chocolate to the base through contact with the lower mesh belt, which has been pre-coated with a thin chocolate layer. Total chocolate deposition is regulated by overflow weirs and return flow pumps. After enrobing, the bars enter a vibrating section, which removes excess chocolate and promotes even distribution across the surface. Next, the enrobed bars pass under dual air knife systems, which blow away excess chocolate and refine the final bar shape. The air knives are positioned above and to the sides of the conveyor belt and deliver high-velocity air streams shaped by nozzles. Air pressure and flow direction are adjustable to control surface smoothing and eliminate drips or streaks. From here, the bars enter the cooling tunnel for chocolate crystallization. This tunnel is temperature zoned, typically starting at 12 degrees Celsius and gradually reducing to 6 degrees Celsius. Multiple air curtains prevent moisture intrusion. The cooling belt is constructed from food-grade plastic or stainless mesh and runs at a speed coordinated with enrobing throughput. Time inside the tunnel varies between 8 and 12 minutes, depending on bar dimensions and chocolate mass. Upon exiting the tunnel, the cooled bars are transferred via synchronized belts to the wrapping line. The wrapper feed system pulls pre-printed film rolls into a forming collar, where the film is shaped into a tube around each bar. The longitudinal seal is created by a heated roller or ultrasonic sealer. Transverse seals are applied at both ends by heated rotary jaws. The wrapping material is a multi-layer laminate typically composed of oriented polypropylene and metallized films for moisture barrier performance. The wrapping machine cuts and seals at rates exceeding 300 units per minute. Temperature, tension, and registration are electronically controlled. Eye marks on the film align the print with the bar position. Any deviation beyond +1 mm triggers automatic correction. Wrapped units are discharged via a conveyor to a belt that aligns them for secondary collation. Depending on format, bars are grouped into twin packs or multi-packs. Mechanical pushers or robotic pickers load grouped units into cartons or wraparound sleeves. These cartons are formed from flat blanks fed from a magazine and folded using pneumatic actuators. Glue is applied at specific points by hot melt applicators, operating between 160 degrees Celsius and 180 degrees Celsius. Carton forming and glue compression are synchronized with product loading to ensure square, tight packages. Each carton is then indexed onto a conveyor for further grouping if needed. Although palletizing is excluded from this explanation, the output at this point consists of individual or grouped bounty bars, fully formed, enrobed, cooled, wrapped, and mechanically packed in a continuous flow operation. The production process is continuous, with coconut mass production, slab forming, cutting, chocolate tempering, enrobing, cooling, and packaging all connected via coordinated mechanical systems. Component flow is fully synchronized. All pumps, motors, conveyor drives, cutting blades, and enrobing units are driven by variable frequency drives and controlled via programmable logic controllers. Sensor arrays track mass, temperature, flow rate, belt speed, and chocolate level at multiple points. Each mechanical action is executed with predefined parameters for precise size, mass, and texture control. At no point is there any batch handling beyond the initial coconut sugar fat mixing phase. Once the slab is formed, the process is entirely linear and uninterrupted. Chocolate is continuously tempered and recirculated. Belt tension and alignment are automatically corrected by sensors positioned at key transition zones. All rotating equipment is balanced to minimize vibration and mechanical wear during high-speed operation. The only thermal processes are the initial cooling of the coconut mass to retain structural integrity during cutting and the two-stage cooling of the enrobed bar for chocolate crystallization. These are separated and isolated to prevent temperature overlap and ensure phase separation between fat-based ingredients and sugar syrups. Production of Baby Ruth chocolate bars begins with preparation of three major internal components: nougat base, caramel layer, and roasted peanuts. Each is manufactured separately in dedicated lines before being combined, enrobed, cooled, and wrapped. Nougat preparation begins by heating a sugar syrup composed of granulated sugar, corn syrup, and water in stainless steel cooking kettles. The mixture is continuously agitated with paddle mixers while being brought to a target temperature between 115 degrees Celsius and 125 degrees Celsius. The heated syrup is transferred via jacketed piping to a whipping kettle. In parallel, a protein solution, commonly egg white solids or milk protein concentrate rehydrated with water, is prepared in a separate mixing vessel and whipped at high speed using rotary whisks to introduce air and build foam structure. The hot syrup is gradually introduced into the aerated protein foam under continuous mixing. The injection is controlled with a metering pump to regulate flow rate and avoid protein collapse. Once combined, the mixture forms a dense but aerated nougat base. Additional flavoring agents, such as vanilla or milk powder, are introduced at this point. The nougat is discharged onto a cooling table or directly onto a continuously moving belt coated with release agent. The mass is shaped into a sheet using roller levelers that compress it to a uniform height, generally between 12 mm and 18 mm. Edge guides ensure consistent width. The nougat sheet passes through a cooling tunnel with forced air at 5 degrees Celsius to 10 degrees Celsius, solidifying the mass to prepare for the caramel layer. Dwell time in the tunnel is determined by line speed and product thickness. The cooled nougat sheet exits the tunnel and proceeds to the caramel application station. Caramel is prepared in a continuous cooker using a blend of glucose syrup, sweetened condensed milk, sugar, and butterfat. The ingredients are heated in a scraped surface heat exchanger where temperature is raised to 115 degrees Celsius, 120 degrees Celsius, allowing moisture reduction and Maillard reaction for color and flavor development. The cooked caramel exits through a static mixer and flows into a deposit manifold. Caramel is applied in a controlled layer onto the surface of the moving nougat sheet. A spreader bar or leveling roller ensures even thickness, typically between 5 mm and 8 mm. The sheet, now composed of nougat and caramel, passes through a secondary cooling tunnel to lower the temperature of the caramel to a semi-firm consistency. Cooling prevents deformation and facilitates cutting. At the peanut feeding station, roasted peanuts are applied onto the tacky caramel layer. Peanuts, previously roasted at 150 degrees Celsius, 170 degrees Celsius for 20-25 minutes, and cooled, are distributed from a hopper via a vibratory feeder. They are released through multiple chutes spaced laterally to ensure even coverage. A compression roller lightly presses the peanuts into the caramel, anchoring them mechanically. Excess or misaligned peanuts are removed by a combination of rotating brushes and air jets. The layered slab, now consisting of nougat, caramel, and embedded peanuts, proceeds to the portioning station. First, longitudinal cutting blades divide the sheet into multiple lanes, matching the width of the final bars. Rotary disc blades mounted on servo arms maintain cutting precision at high speeds. Next, transverse cutting is performed with guillotine knives that are synchronized with belt speed to produce exact bar lengths. Standard bar length ranges between 80 mm and 100 mm, depending on pack size. Each individual bar is spaced out on a conveyor and conveyed to the enrobing line. Enrobing is performed using milk chocolate prepared in tempering units. Solid chocolate blocks are melted in jacketed tanks at 45 degrees Celsius, 50 degrees Celsius. Melted chocolate is tempered using a 3-stage heat exchanger that brings the temperature down to 28 degrees Celsius, 30 degrees Celsius, before raising it slightly to 31 degrees Celsius, 32 degrees Celsius, optimizing crystal structure. Tempered chocolate is pumped to the enrober and flows over a curtain that uniformly coats the top and sides of each bar. The underside is coated by the bar contacting a chocolate film spread onto the mesh belt. The enrober uses a closed-loop recirculation system with a filter to remove solid debris such as peanut fragments. Chocolate viscosity is continuously monitored and adjusted by recalibrating the temperature or adding cocoa butter as needed. As the enrobed bars exit the curtain, they pass over a vibrating section that removes excess chocolate and evens out the coating. Air knives located above the belt blow off remaining drips and define the shape of the chocolate coating. Decorative top striations are formed by additional nozzles or vibrating wires that create surface patterning before the chocolate solidifies. Coated bars enter a cooling tunnel that is divided into multiple thermal zones. Temperature decreases gradually from 12 degrees Celsius to 5 degrees Celsius along the tunnel length. Air is dehumidified to prevent condensation and maintain surface gloss. Conveyor belt speed is regulated to maintain a dwell time of 10-14 minutes, allowing full crystal formation within the chocolate and ensuring coating integrity. After cooling, bars exit the tunnel and proceed directly to the wrapping system. Horizontal form-fill-seal machines handle individual wrapping. Printed film is fed from a roll and shaped around the bar using a forming collar. Longitudinal seals are made with heated rollers, and transverse seals are applied with rotating jaws. Seal parameters are set according to film type, typically biaxially oriented polypropylene. Eye mark sensors on the wrapper film ensure print alignment with bar positioning. Wrapped bars are discharged from the flow wrapper and directed onto collection belts. Depending on final packaging format, bars are grouped into singles, multi-packs, or inserted into cartons. Collation is handled by diverters and indexing conveyors that control product spacing and group counts. Cartoning is performed using automatic cartoner machines that erect, fill, and close cartons in one continuous motion. Hot melt glue is dispensed by nozzle applicators to seal carton flaps. Carton size and closure mechanism are adjusted based on product format. At this stage, the complete Baby Ruth bars have undergone mechanical and thermal transformation from raw syrup, milk solids, and nut ingredients into structured, layered, enrobed, and wrapped units. From initial syrup cooking to final wrapping, all steps are continuous and synchronized by servo-driven machinery, sensor-guided conveyors, and recipe-controlled dosing systems. No manual handling is present between slab formation and wrapping. All ingredient transitions are facilitated through pumps, screw feeders, and belt conveyors. Mixing, cooking, spreading, cooling, cutting, coating, and wrapping occur in physically distinct but functionally integrated process zones. The nougat structure is controlled by syrup concentration, aeration speed, and protein matrix strength. Caramel consistency is determined by temperature profile and solids content. Peanut adhesion is achieved by compression into a semi-set caramel phase. Chocolate crystallization is stabilized by controlled tempering and gradual cooling. Final bar geometry is maintained by precision portioning and belt tracking. Line speeds are configured to produce hundreds of bars per minute, with each step calibrated for thermal load, product viscosity, mass consistency, and dimensional tolerance. The entire operation functions as a continuous flow line driven by precise thermal, mechanical, and depositional parameters. The result is a consistently shaped, layered, and enrobed chocolate bar manufactured through a sequence of interdependent, high-speed industrial systems.